Hello! Oh, hello, too loud. Oh my goodness. Okay, so nobody could hear any of that because I had muted my microphone. Hello, welcome. The first 2 minutes of this video will be me doing this. I didn't actually say anything important, and I said a few things that were embarrassing, so I'm glad that didn't actually happen. My name is Dan. This is the Coding Rainbow, a live stream about programming and stuff. Creative coding, different topics, etc., etc. I've lost my train of thought, the little audio thing. Oh, let me know if you can hear me now. Yes, I have a new haircut. Thanks for noticing. I am live streaming to 3 outputs right now. YouTube, which is what I'm looking at on my little preview screen here, and I see a chat going on. I see people commenting. I am also live streaming to Twitch. I pretend to know what Twitch is. I'm going to check to see. I don't actually see myself on Twitch in my preview. I'm going to refresh this page, but who knows if it's working or not. And then Facebook, in theory, the Facebook, yeah, it says I am live streaming to Facebook. I'm not going to watch that, but now I feel awkward and confused. And I'm going to go back to my, come back here to YouTube. Okay, so I'm going to make this chat much larger so I can see it in the out of the corner of my eye. Okay, so welcome. Let me, so first of all, if you're watching this video in an archive, you can't do this if you're watching it live because the future does not exist yet. But if you're watching this in the archive, take a look at this video's description. It will have time codes in there that you can click on to get to various parts. I expect to be here for approximately 2 hours today. I'm sure I will perhaps take a short break somewhere in the middle. I have not gotten my Muzak thing going where my music will play during the break, but we'll get to that later. But today's session, I have decided, based on some feedback and suggestions and various things, will be all about algorithmic botany. And what do I mean by that? I mean looking at different strategies and techniques for generating plant-like things, leaves, trees, flowers, those types of things through algorithms and code. And I'll do just about everything in JavaScript. I do want to use processing, which is a Java-based programming environment, for the 3D thing that I want to do. I might try to do that in JavaScript, but I know, anyway, well, I'll see about that once I get to the sort of 3D part. But mostly I'm going to stay in JavaScript in the browser and show you some sort of classic algorithms, how they work, go through them. I'm also going to, as I do this whole live stream, oh, and I need to record. This I always forget. I'm going to now record my own personal backup archive. So I'm hitting record now to do that. And so this backup archive that I'm recording to disk over here, my magic computer thing over here, this I will also use to chop up and make some standalone video tutorials that will appear on my YouTube channel. So it's Friday. It's about to be Memorial Day weekend here in the United States. It is very hot in New York City. I'm wearing a t-shirt and I have a haircut. There are some very bright halogen lights in this room. I'm at the School for Poetic Computation, which is a independent school thing where lots of interesting, exciting things happen. I would encourage you to check out their URL, sfpc.io. And their summer program is starting up next week. So I'm still going to be doing my live broadcast and video tutorials, but there'll be other people in this space. So that'll be interesting. Maybe we'll just bring people in and say hi and shake hands and talk, and then I'll just leave and somebody can come in and talk to you and all that sort of stuff. I don't know, it's magic will happen next week. The other thing I would like to mention, I'm not live on Twitch. So I don't know why the Twitch is not working, the Twitch, but unfortunately there's not a lot I can do about that right now. So I guess I'm gonna have to leave that off for today, unfortunately. So take a look at YouTube or Facebook and I'll look into what's going wrong with Twitch and see if I could fix it later. Apologies for that. Okay, so the other thing I want to mention, sheepishly, but I think it's important to mention, is that, let's see here. Let's see if a Google search comes up for me. So I opened something called Patreon. I started a Patreon thing. I'm gonna search this. Look, by the way, here's another great a YouTube channel, Coding Math, that does a lot of similar tutorials. Probably has a lot of similar topics. It's great. I encourage you to check that out. So I don't see where my, so I'll just go to here. Oops, hold on. How do I guess I'll have to log in. I probably have some like crazy password. Let's see if this works. What's the chance I used like sort of a normal password for this? Very little chance. Okay. Okay. Let's see here. Let's look up. If people are really upset about, I see people still mentioning the Twitch thing in the chat. I will investigate. The issue with that is I have to like turn this off and turn it back on, because if the other streams are working, then it's sort of like there's it's set up to stream to Twitch, and I don't know why that's not working. Okay, boy, I did not set this up very well. Okay, wait. I'll just go to my Twitter page, and somewhere in here, I posted a link. There we go. So I don't know how you find this. I need a good link to it from the description. You can look at this crazy URL up here. I don't know if there's a way to get like a permalink on Patreon, but what Patreon is, I feel like I'm... sorry, I'm doing too many things at once. Deep breath. Hello, I'm back. It's super hot in here. I'm starting to feel a little faint. Okay, back to talking to you, the person on the internet. Okay, Patreon is a service, much like it's in some ways similar to Kickstarter, or it's a crowdfunding service. But the idea is that you can pay a monthly or a fee to somebody producing content regularly. So 100%. Only if you feel so. My content is meant to be free and online. And I am experimenting with different mechanisms for different ways of making this sort of a sustainable project over a longer term. I've tried looking at it, I turn the YouTube ads on and off every once in a while to see what that does. And now I'm looking at this sort of Patreon system to see how that works. So if you're interested, I want to get to the content today. Maybe later I'll come back and talk more about Patreon. But if you're interested in supporting this project through Patreon and you can't find the link, just tweet me. I'll send it to you. Okay. Blah blah blah. All right. So this is what I want to do today. Let me look here and see if everything is working in a few different places. Again, lots of people are asking if you can't watch right now. This entire thing is being recorded, and it will live forever, or until the robots take over and delete YouTube, it will live on YouTube. And I'm keeping my own backup in various locations in case that becomes a problem. So when the robots take over, I will have my hard drive of all the backups of all my videos. Okay, so today's topic, let me come over here for a second just to use this whiteboard for a second. So what I want to look at today and do a set of tutorials about different ways of generating trees with code, just to put it right there. So the first way that I'm going to look at, which I think will be a simple program, and I do actually have existing video tutorials already about this. We'll sort of start fresh and do it again in JavaScript, but is just to look at, so I'm going to make a sort of list here. It's just to look at fractal trees with recursion. And then I think, so this is sort of the basic idea, right? I want to draw a branch that's connected to two branches, that's connected to two branches, et cetera, et cetera, et cetera. The other thing I want to discuss related to that is the idea of having a single function that just sort of generates the pattern and draws it, kind of instantaneous, immediate drawing, versus the idea of a list of objects. And this would allow you to add physics to that tree. So there's one, you can think of this as, what's the difference between having like this rubber stamp, I don't know if it needs to be rubber, a stamp that just stamps the tree pattern and you see it and you can't do anything to it, versus creating a data structure that holds all the information about the tree so that you could draw that tree, but you could also delete branches, add leaves, make it sway, that sort of thing. So that's number one. The other thing I want to look at is something called an L system. L stands for Lindenmayer. We'll look up his first name. A botanist who worked out some algorithms and strategies for generating, for modeling plant growth cellular growth. Look at that. It involves, and one of the nice things about this is it involves strings and text and recursion. So there's a lot of like interesting programming computational skills wrapped up in there. And then for the grand finale. Oh, and I've already, somehow the cameras have been, what? This is going to go off in 3, 2, 1. It didn't do it. I'll just turn it off and on for a second. These cameras go off after 30 minutes. One day I'll fix that. Oh, anyway, it's back now. So is something called space colonization. This is something this is nothing new. I think there's the paper that I was looking at is maybe from 2007 or 2005. But this was new to me as of earlier this week. So this is an interesting algorithm that allows you to generate sort of the veins of a leaf or tree structures in a very different way from these other ones. And so I want to implement that as well. So all of these, so this should be like there'll be like 4 videos here. 4 little tutorials. I want to do them one at a time, and I'm going to write the code for all of them from scratch, I think. So that's kind of the plan, and I'm going to do it all in JavaScript in the browser with P5.js. So that's kind of my plan. I'm going to go check out the chat now to see if anybody has any comments or questions. Okay. Okay, excellent. All right. So let me mention a couple other things that have come up a lot recently. One is, let's say you have a question. Where can you ask that question? Where can you get help in terms of programming? So there's a variety of places, but for the stuff that I'm doing, there's a couple things. One is you can write in the YouTube comments. I try to go in and answer them, but there's also other people answering them there. The place that I would suggest that you write questions is forum.processing.org. There are a lot of different categories, but I want to point out for those of you who aren't aware that there are forum threads also now for P5.js. So for some of the stuff that I'm doing today, if you have particular questions about P5.js, you can ask them in the forum there. I periodically look at the forum and try to answer stuff there, but there's tons of people with way more knowledge than me, and they're also answering questions. So hopefully you'll get a friendly face and a supportive reply. If you find a bug or issue with P5.js or processing that's not working or something, that's where you can go to GitHub and file a GitHub issue. And in the last live stream, I kind of went through that a little bit, so I'm going to not do that again right now. But it's one of my personal missions in life is to help, it's a desire for people who want to use GitHub to feel comfortable using GitHub. So if you're having trouble with that, please let me know. And I have also some Git and GitHub tutorial videos. Now, you can also ask questions right now in the chat, and I'm not looking at it always, but there'll be points of time during this live stream that I will say, hey, I'm going to go look at the chat, and that's a place to ask a question. If you're watching this on Facebook, I don't know why you're watching this, but if you're watching this on Facebook, I'm not really looking at the comments there, but I will look at them later. I have a new thing, which is that I'm experimenting with a Slack channel, but I am opening the Slack group only to people who subscribe to the Patreon. So that's one way, and that's something that has a small group right now of just 10 or 15 people, and I'm kind of hanging out there and answering questions and discussing stuff about creative coding as well. So that's kind of just sort of a landscape of places just in terms of asking questions and getting extra help. Okay. So one question, somebody writes, handwriting is a bit small on the whiteboard. Let me take a look at that. Okay, that's good to know, thank you. I will write larger, but mostly I'm going to use it for diagrams and not words, so I think that'll be less of an issue, just kind of making that list right now. Do you also cover fractal trees and L systems in your Nature of Code course? Yes, so you may be wondering, hey, don't you already have stuff about this? And I do, and I'm just kind of doing it again and trying to discover some new stuff with it. But one thing I'll mention, if you go to natureofcode.com, which is this particular URL, and go here under Read Now, under Chapter 8. Chapter 8 really is where you can find information about fractal trees and L systems, and also this second question about the sort of like list of objects thing. In the Cadenze course, which is an online course running now through a separate company, I think session 4 is kind of about this stuff too. Yes, so those things exist, and now this exists too. Okay, so I think I'm ready to get started. Let me get set up here. I'm just going to kind of like check and see. I want to see very briefly if I can fix the Twitch thing. So I'm going to just really quickly look over here. Output settings. Let's see if I can hit OK. OK, I see the issue. For whatever reason, it didn't authenticate with my password. So let me see what my password is. OK, I got it. So unfortunately, this is really my mistake. I'm vaguely tempted. So I think it was my mistake, or like my password wasn't saved and the Twitch thing actually didn't start. So Twitch is not broken. It's on my end. I'm tempted to hit stop and then hit stream again, but let me see what I've got here. What's working and not working. So currently, there are a few people watching on Facebook. And I lost my YouTube dashboard. I have, let's see, ignore. Oops. It's a lot of stuff. Should never look at this. Okay, I've got people here on YouTube. So I think what would be best, I hate to say this, is to leave Twitch off for today. And if for some reason things crash and aren't working well, then I'll turn the stream off and turn it back on. But for now, I'm going to do that. Oh yeah. So somebody asked. So okay, all right. Maybe later I want to talk more about the Patreon and get your feedback about it. But in the Patreon has this thing for rewards. And currently, I just made up 2 levels, like a $5 level and a $10 level. I guess I didn't. The Slack channel is with the $5 level, and yes, it's also with the $10 level. And I think I might, based on some feedback, I might just really just have one level, and you kind of get everything with that one level. But I know I'm thinking about that. But yeah, the Slack channel is for anybody who contributes, really. And I'm not really trying to do. I feel so strange about these things, but my idea is not to make this like really a closed thing, but to give an opportunity for people to have a smaller group for discussion. It seems like a good model. Sort of see how that goes. Everything's an experiment. Okay, so yeah, the question has also been asked in the chat about the sort of neural network chapter in Nature of Code. So I mentioned this on a previous stream, like a few weeks ago, probably. This neural network chapter is, I would say, very basic, a little bit outdated, not the strongest chapter in the book, and I have plans to redo it. And all of my plans to redo anything or to work on anything else, I've kind of gotten sidetracked because I'm really focusing on trying to make these videos. And strangely, it takes a lot more time and energy and thought than I had anticipated. You can't just really just show up once a week and turn it on. So, but I will hopefully get to that. And I think what would help is if I plan and set a date to actually do some of the new material I'm imagining for the neural network section in a live stream. Okay, I spend too much time doing exposition. We're about 20 minutes in and I want to get started. So I'm going to keep an eye on this. I'm going to keep an eye. I got the chat a little bit bigger over here. I am going to close this. And now, okay, so one thing I did which is really exciting is I configured my Atom editor to have the same shortcut key as processing's auto format. So processing, this thing over here, processing up there, it wants me to install some sort of update. Processing has this auto format feature which auto indents and auto spaces out your code. This is a thing that gives me a source of great happiness and serenity in life. And I have this I've been doing it for probably 10 plus years. So I just can't help but type code and hit Command T, Command T, Command T. So finally I figured out, and now I'm trying to use this Atom editor, which is I believe an open source project. maybe that came out of GitHub. Anyway, but it's a generic code editor that you can use, and I'm going to use it in the tutorials today. And I added a package. If you don't know, you can go to packages. I added a package called Atom Beautify, and I believe if you want to add packages, probably under preferences there's a way, or packages, somewhere in here there's a way to add a package. So I added it, and then I went to the preferences and I did a key command thing. I can show people how to do that at some point. If people are interested. Everyone's complaining about my short hair. Look, it's 90 degrees, and my hair grows very fast, so it'll be back. It's pretty short. Okay, so let me get set up here with a folder today. So I'm going to call this folder Algorithmic Botany, and I'm going to put just a generic folder in there, and I'm going to call this Fractal tree, and I'm going to open this up in Atom. So we're getting started here. I can look at the sketch. How's this for a font? Oh, let me just add this in here. Function setup, function draw. How's this for a font size for people and sort of colors? Is it sort of readable? Okay, let me know. Okay, now we're getting close to doing something. I got to get terminal going. So one thing I'm doing, just so if you're wondering, is I'm going to run a local web server in the background to serve up the files that I'm working on code-wise today. And this is something that I have a whole separate video. If you Google shiftmin local server on YouTube, you'll find it. So I'm going to use Python, a Python command to run a little local server. And you can see that it's running it on IP address 0, port 8000. So I can minimize this now. And if I open up a web browser, like Chrome, and go to localhost, and go here, we can see there is my code running, and I've got a JavaScript console over here. So I'm just getting myself set up to do the first example. And yeah, okay. So so that now I'm getting on. Now let's make sure things are really working. I'm going to say create canvas 400, and I'm going to just give it a background. If you want to watch this, okay, hold on. I'm going to make that spacing do this, and make this spacing do that, and do something weird here. And now, magic! Here it comes. I need a drum roll. I need a list. I need a whole soundboard, various sound effects, because I want my drum roll sound effect now. Command T. All right, I don't know. That wasn't nearly as exciting as I had imagined. Maybe with sound effects, look, it's all nice and indented. I've said this before, but don't be like me. Live with code that is a mess, with weird spacing and weird indentation. Your life will probably be better than me, who must have it indented properly, otherwise beads of sweat, anxiety attacks, all sorts of things can happen. Okay, just so you know, Command T is not the built-in shortcut of Atom. You need to install this stuff, and if people are interested, ask in the chat later before I leave. I will show you how to install this stuff. But for right now, I want to get to my list over here. Okay, so what are we going to do? The first thing, okay, so let's bring up something here. I'm going to go to a website. If you're not familiar with it, this is a website called algorithmicbotany.org. And look, I have a link to, at one point I was doing a presentation and I wanted to show an ITP project. This is a great project, but I'm going to remove this now. I'll show it another time. Okay, and I don't need this bookmarks bar or whatever, it's fine. So this is a website that, let's see. Oh, it's from the University of Calgary, the Department of Computer Science. There are a lot of papers. There's a book, I believe, called The Algorithmic Beauty of Plants. It might be out of print. I have a copy of it. I wish I had it here to hold up. It's a beautiful book. And it's just, this website houses a variety of papers and research links and resources related to algorithms for generating plants with code and math. And so there's tons of nuggets there. And I will Oh yeah, here's a link to the Algorithmic Beauty of Plants, which I believe actually now you can see the entire book is actually available online as PDFs and stuff. So graphical modeling using L systems is chapter 1 where that book starts. And that's on my list here to really get to and spend a lot of time. This is sort of like a warm-up in my mind, the fractal tree thing. It's kind of, and I feel like maybe it'll just be a short, like quick and dirty 10-minute thing. But I think it's worth doing today as a little bit of a warm-up and just kind of like look at these different systems in context. So I want to mention that this exists. I want to mention that this exists. I encourage you to take a look at it. Find different algorithms in there, send them to me. I'll come back to them in other videos and that sort of thing. Okay. Okay, so I think I'm ready to begin. So the first thing I'm going to do, let's get a visual reference. You gotta love Wikipedia. All right, this is good. This is basically what we're looking for. Okay. The first thing I want to do is basically just implement this. So I want to implement it first using transformations, translate, rotate, push, and pop. And then after that, I want to implement it using trigonometry. So sine and cosine, and objects that can move and change. So I'm going to do it 2 ways, and then it'll be 2 different video tutorials. I don't know. I'm trying to think. OK, I'm going to get to something soon enough. It's been a half an hour so far. So here's the thing. I'm trying to think of how to best organize this, and I'm not going to worry about it. This is going to be a series of coding challenges. These will probably go in the coding challenges playlist, and they'll be this first one will just be fractal tree. Okay, this one, this might be a basic review for some of you. I'm checking out the chat here. Everybody can hear me still and see me okay? I'm just going to look over here real quick to make sure everything's working. Okay. And I'm about to, okay, got to get the chat up here. Okay, here we go. Okay, so I'm going to cycle the cameras. And checking my battery levels on the microphone, and I'm ready to start. Now, musically, I sort of think, okay, I've probably done this like a whole bunch of times, but I haven't actually programmed this from scratch in a while. I just always like show my example and explain it. So this could go horribly wrong, but that'll be interesting to see what happens. So in this particular first video, what I need to do is explain the concept of recursion and then write a recursive function that does this tree thing. I need to get, sorry, a Kleenex. You can see that, which I have over here. Okay. For some reason, feels harder to do on a Friday. I did this earlier this week on a Tuesday, and I feel like my brain and everything made sense to me. I had all this energy, but okay. All right, here we go. I need this button to be over here. Okay, excellent. And so let's see how this goes. Sorry, everybody. I swear I'm going to start. I want to, I think I'm going to have this be clean to start with. Okay, here we go. And a 1, and 2, and a 1, 2, 3. I don't know why my nose is running all of a sudden. Allergies or something. Okay. Hello, welcome to another coding challenge. In this coding challenge, I am going to build from scratch in JavaScript a fractal tree. And I'm going to do kind of, you can see once this video is over and I've made one example of it, you can see sort of a variety of images here of things you might be able to make from it. And you'll also see that there are a few different follow-up videos after this one that show other techniques for generating trees in different ways. But let's just get started. First, let me just draw you a diagram to sort of, so that we can kind of understand what's going on. So the core idea of a fractal tree is we have a recursive definition. So what is a recursive definition? A recursive definition is something that's defined in terms of itself. And actually, there's a math function, which is known as factorial. 4 factorial equals 4 times 3 times 2 times 1. 10 factorial equals 10 times 9 times 8 times 7 times 6 times 5 times 4 times 1. Now, 3 factorial is equal to 3 times 2 times 1. So you could actually say that 4 factorial is equal to 4 times 3 factorial, or that any number n factorial is equal to itself times n minus 1 factorial. And this is a recursive definition. I'm defining factorial in terms of itself, which seems like something you shouldn't be allowed to do, but it is something you are allowed to do. In fact, you're encouraged to do, and even though you might sometimes get a headache, all sorts of wonderful, beautiful, elegant things can arise out of recursive definitions, one of which being fractal trees. Okay, back over here. That was completely unnecessary, but I did it anyway. So what is the recursive This is like some math stuff and some numbers. What does it mean to have something that's visual defined recursively? Well, we have this idea of a branch. So I'm going to say a branch is a beginning and end point. And it is defined as having 2 branches attached. You probably can't read that, doesn't really matter. This says branch is defined as a line that has 2 branches attached, like this. So let me draw that over here. This is a branch and has 2 branches attached. Oh, but these are also branches, so they have 2 branches attached. Oh, and these are all also branches, so they have 2 branches attached. Oh, and these are all also branches, and they have 2 branches, et cetera, et cetera, et cetera. So a branch is defined as something that has 2 branches, and those are branches. This is known as recursion. Now, one thing you might be thinking about is, where does this end? So in the theoretical, magical world of fantasy, this would go on forever. And these branches are getting shorter and shorter, and they would get infinitely small. But in the world of pixels and programming, we have to stop somehow. So we need an exit condition. And actually, that's built into this up here. I just didn't explicitly state it. Whenever you get to 1, you stop counting down in this multiplication for a factorial. And the same thing is true here. We could say continue branching. Each branch has 2 branches attached to it until it is less than some number of pixels long. So this is the idea. And the way that this ends up happening in code is if you have a function, whoops, that's not how you spell function. In code, if you write a function and you call it something like branch, a recursive function in code is defined according to itself, meaning somewhere in that function, you're going to actually call itself. So you're calling the function you're defining from within the function, and it results in this sort of loop. I'm going to call branch, which calls branch, which calls branch, which calls branch, and eventually stops at some point. So this is the idea of recursion and how it's implemented in code. Let's go and actually write this code now. Dare I say, I'm a little bit afraid to do this, but let's see what happens. Okay, so what I have here is a P5.js sketch. P5.js is a JavaScript framework. Links in the video description of where you can get it and get started with it. And the only thing that's going on right now is that a HTML5 canvas has been created, and I'm drawing a gray background there. So I just want you to be able to see that. I'm going to go back to over here where I'm running it, and you can see, you can see there's my 400 by 400 pixel background. So I want to have the trunk of the tree to start with. So just to kind of get that going, let's draw a line that goes from the center, 200, and the bottom to the center, and the bottom minus some length. So I'm going to make a length variable which starts at 100. And now, and this line, I want it to be white. And so now if I run this again, you can see, okay, I've got a line at the bottom. So I have the trunk. So what I want to do now is actually put that code that's drawing the trunk into a function. So I want to call branch, and branch is actually going to draw that line. So let's do that. So the next thing I'm going to do is make this a function. And one thing I want to do with this function is I want to give this function an argument, and that argument is how long to draw that branch. So I'm actually going to put that variable here in the function, and then I'm going to say line 200 height minus length. So whoops. So now here I actually want to, and I'll just say stroke 255 here. Now what I want to do is say branch, I forgot what I was doing, 100. So you can see here that the idea here, same result, is that now I'm calling this function branch, and I'm giving it the value 100. Now, here's the thing. The way that this is going to work is I don't actually want to, let me come over here. Now, pretend this is my canvas. What I did is I said, oh, wrong side of this pen. What I did is I said, here is the x location 200 comma height. And what I wanted to do is draw the line from here all the way up to here. But what I want to do is I want this actually to be 0, 0. So one of the things that I'm going to do in this particular example is I'm going to use the p5 function translate to sort of move the origin around and always be drawing from that origin point. So actually what I want to do is translate. Oh my God, I've lost my mind with this pen. It's a double-sided pen that's of doom here. This doesn't fit. I don't know, maybe it goes on this side. There we go. Okay, so what I want to do is the 0, 0 point here, I want that to start here. And you'll see why. It'll make more sense in a moment. Oh, I was in the wrong place the whole time, arg. Okay, hold on. This will get edited. That was a terrible explanation anyway. And I'm sorry to Mathieu, who is helping me with editing when I really screwed something up. I think that was unfortunate. So I'm going to go to the point where I meant to. I got to work on this button. I'm going to go to the point where I meant to go over here. And it will get, this will somehow get edited. I don't believe in editing, but except in dire technical circumstances. I don't know what this is going to do. Oh, I'm in the wrong place again. I'm over here. I'm trying to erase what I drew. Okay, everything's going to be okay. All right. Okay, so I'm going to pretend I'm going over there now. Okay. Yeah, I could get a, I should use a sensor. I totally should have it changed based on a sensor of where I'm standing. That would be a great project. I will do that at some point. I like that idea. The only reason I kind of like the button is I can change it without moving if I just wanted to refer to something over here. Now the button though is getting a little bit iffy. It's like not working exactly right. Okay, so I'm gonna go over there again. I forgot what I was talking about. It'll be fine. So what I want to do is actually, instead of drawing the tree starting at this bottom location, which is 200 comma height, I want to move the origin, which is here, all the way down to here. I always want to be drawing the branches relative to the origin by using the translate p5 function, which sort of moves that 0, 0 point around. And once we start doing a little bit more of this, you'll see why that makes a lot of sense. So let me come back over to the code. And what I'm going to do is right here, I'm going to say translate to 200 comma height, branch 100. And now this becomes draw a line from 0, 0 to 0 comma negative length. So now if I run this program, same exact result. So we have a very simple beginning. We are translating to the bottom. We are drawing a branch from the bottom straight up. So what do I want to do next? I have drawn a branch from the bottom straight up. Well, guess what I want to do? I want to rotate and draw a branch to the right. So what I want to do is now say, let me rotate by 45 degrees. Let's start with 45 degrees is pi divided by 4. And then let me draw another branch, 0, 0, 0, negative length. Oh, you know what? I also need to translate. So before I'm down here and I drew the branch like this, and now I want to start drawing from here. So after I finish drawing the branch, I need to translate back up to here. Okay, so before I rotate, now I need to translate up 0 comma negative length. So we're drawing that bottom line, we're translating up to the top, we're rotating and drawing another line. Let's see what that looks like. There we go. Second branch. Now, I want that second branch to be a little bit shorter. So maybe I'll make it 2/3 of its size. So multiply it by 0.67. So you can see now it's a little bit shorter. But have I done anything recursive here yet? So am I really going to go and draw every single line of the tree as a separate line function? No. What do I actually want to do? I just want to call branch again. And what do I want to call branch? With a slightly shorter branch. Now, I'm tempted to run this. And I could run this. But if I run this, my browser's going to crash most likely. Let's just try it. Danger, danger. Let's live dangerously. I'm going to run this. So you can see, good, we got an error. Maximum call stack size exceeded. So what happened here? You can see it started doing it, but it just like decided it couldn't do it anymore. What happened? It's calling branch from within branch, and that's an infinite loop. Branch calls branch calls branch calls branch calls branch. So I need to say at some point, don't call branch anymore. Where every time I call branch, length is shrinking. So I could actually just say something like, only if length is greater than like 4 pixels should I actually bother calling branch again. So now you can see here, I'm drawing the first line, and then I'm calling branch again and rotating, calling branch again and rotating. So, and we could see here, I could continuously, I could make that angle of rotation a variable. So I said it was pi divided by 4. And I could rotate by, I'm going to call that angle actually, by an angle. And one thing I could do, just so you see, is I can make a slider. Let's just do this really quickly. There is a P5, in the P5 DOM library, I can make things like a slider. And I want to have a slider from 0 to 2 pi. Oops, I can't spell. How do you spell 2 pi? And I want it to start at maybe pi divided by 4. And then what I want to do is say in draw, angle equals slider.value. So what I'm doing now is if I run this, create slider is not defined, probably because I need to actually reference the DOM library in the index file. So now you can see, whoa, oh, look at this. So one thing, by the way, it's working, but notice how the slider, it can only move up by units of 1. So one thing that I forgot is there's an argument. There's a fourth argument, which is the step size for the slider. So I want to move it up by like lower increments. And you can see here, now I can sort of play with that angle, and I can turn what that angle of rotation is for this tree thing. But I've only branched to the right. Now, there's a couple issues. One is this, why do I have this pi is not defined error on sketch line 1? You know what's sort of strange is, is that actually, this is sort of a little weird thing, but pi is a built-in variable, part of the P5 DOM library, the P5 library, not the DOM library. And the P5 library, none of its stuff is available in setup just yet. But it doesn't really matter because I'm getting it from the slider. So let's change that to 0. So I can go back and we can see, okay, so now I have this tree that I can change the angle with this slider. And you can see all the way from 0 to 2 pi. And I probably actually just want to make it from 0 to pi divided by 2 or whatever, but we can change that range later. Now, that's only branching to the right. So what if after I branch to the right, I also then rotate by negative angle and branch to the left? Now, really what I want to do is actually have this if statement around all of that. So the idea here is that for every branch, here's the recursive definition of a branch. Draw a line, and then, as long as it's still long, rotate to the right and draw another line, rotate to the left and draw another line. And do that for every single branch. Let's run this. It's not going to work, and we'll figure out why. Ooh, it did something kind of interesting and crazy. Look at this crazy thing. Now, do you see what's happening? Everything is connected. Everything is connected. It's like this. What did I do? I went like this. Wrong side of this pen. I went like this, and then I branched to the right, and then I branched to the left, and then I branched to the right of that until I don't know what I did, but I'm always going, whatever that recursive order is, I'm always going from where I left off. But actually what I want to do is I want to go to here and branch to the right, and then I need to come back here before I branch to the left. And then this branches to the right, and then come back here before I branch to the left. So the way that I can come back is by using the push and pop functions in P5, because push is a function that says save the transformation state. So if I move from if I translate from here to there, and then I say push, I save, I can draw this to the right, then I can say pop to restore, and then draw this to the left. So if I come back to the code, you will see that all I need to do is add a push right here before I rotate and branch, and then also, and a pop right after, and also around here. So the idea here is that for every single branch is defined as a line, and then when you get to the end of that line, you save where you are and branch off to the right, restore where you were and branch off to the left. Now the way the order of things happen is not exactly that, because once you call branch, you're then into the next one, and then you're into the next one, and then you start popping back all the way. I encourage you to try to do some sort of acted out physical demonstration or drawing, try to be the computer following all the pushes and pops. But you'll see now if I run this, I believe it will work. And you can see now we have this lovely fractal tree, and I can sort of change the angle. Now, this is really finished. I've only really scratched the surface here. There's a bunch of things that I might encourage you to think about doing. Number one is, can you keep track of which level of the tree you're on and draw the branch with a different thickness using stroke weight? So that's an interesting problem. I'd be happy to demonstrate a solution at some point to that. You might think about, well, what if the angle isn't the same with all of those branches? What if there is a variable number of branches instead of always two, always with equal angles? And you can see that in this Google image search for fractal tree. You'll see that you can, with various other ways of kind of doing this, you might be able to start to get different types of more chaotic or in some ways organic looking qualities rather than this very exact, perfectly symmetrical fractal. So this concludes this part of just doing this basic fractal tree. I'm going to do this again in the next video, in another video, but instead of using push and pop and translate, I'm actually going to use sine and cosine and some math, and you'll see what doing it that way allows you to do something a little bit different, which might interest you based on how you could then modify the tree at a later point. Okay, thanks for watching, and I'll see you in another video, maybe, or maybe not. Goodbye. Okay. All right, everybody. I don't know. I don't know. I need to drink some water. It's very hot in here. I gotta get some different lights. Okay, this is gonna explode. Everybody, this is exploding my seltzer. That was an exciting moment. I'm sure we could do some kind of programming simulation of why that happened. Okay. So that was video number 1. We're at 50 minutes here. So I want to do another video where I'm going to redo this entire thing, but I'm going to use sine and cosine, and then I'm also going to turn all the branches into objects, which will allow you to animate growing the tree and also place leaves on it. Okay. Okay, here we are. So let me get myself set up for that. So what I'm going to do now is take this, and I'm going to do fractal tree array. I'm going to call this one fractal tree array. And I'm going to open this now with Adam. And I'm going to go back to here, and we can see this here. Okay. So what I want to do, sorry, I'm thinking about this. What I want to do is I want to make an array that has objects in it, and the objects' positions will be defined by sine and cosine. Okay, I'm just going to do this. I'm thinking about it too hard. Okay. All right, summertime. Okay, so one thing I'm going to do is, you know what? I'm just going to do it from scratch. Okay, so I'm moving on. Any questions? Oh yeah, somebody asked, you could extend this into 3D. That might be a cool idea. You absolutely could extend this into 3D, and if I can get through all of the topics I intend to get to today, boy, it's a lot, and a lot of programming, I'm going to do a 3D version of something at some point. But I essentially just have 3 more examples to do, which I think, given that it is 2:30, it's realistic. I'm at least free until 4, if not longer. And I'm just, at some point, I might need to like go get a little fresh air, cool off in here. But such is life. Okay, so I am going to now start this one off. You know, one thing I'm going to do, by the way, is I just want to change. I think this would be better just to have this actually, the range be that in the middle, and then sort of like a little bit. Okay, so I can use the slider to change the angle. Okay. Okay. Okay, here we go. Ready? Fractal tree video number 2. I got the chat. So a couple people are asking about the Patreon. There is a Patreon. It is ready. I'm thrilled for people to support it if you feel so inclined. I don't want anyone to feel any pressure. I welcome you. I love it. Just watching the videos and participating in the processing and creative coding community is great. If you feel so inclined and to support the Patreon, that's great too. If somebody in the chat could put a link to the Patreon, and if also somebody could, I wonder if anyway, please feel free. Okay, here we go. I think everything's still working. I'm going to go on to the next one. Hello, welcome to another coding challenge. This one is a follow-up on the previous fractal tree coding challenge. One of the first things that people often ask me when they first see a fractal tree is, oh, I want it to grow from the bottom. So how do you have it grow from the bottom? This is also the same question as, oh, I want to put leaves on it and then have the leaves fall. So while the fractal demonstration I did in the previous video is a good demonstration and a useful technique, you might need a different way of creating the tree to be able to do more types of animation-like things with it. And the way of doing that is to, rather than draw the tree all at once in a recursive function, is to actually build the tree out of objects. So what I need in the tree, it's over here, I'll just use this as my reference, is I want to create an object that's a branch object. And the branch object only needs 2 things. It needs a start point and an end point, and a display function that just draws itself there. So let's look, and I'm going to build from the previous code, and I'm going to just from scratch take the previous code, which draws this fractal tree, and change it into something that uses an object, branch objects, and an array. Okay, so let me go back to the code, and here we are. And one of the first things I'm going to do actually is just create a new JavaScript file. I'm using the Atom editor with the P5.js JavaScript framework, but there's lots of different ways you could program this. And I'm going to say new file, and I'm going to call this new file branch.js. And then I'm going to go into index.html and make sure I include a reference to branch.js. So now I have 2 JavaScript files I can work with. And what I'm going to do in branch.js is I'm going to write a constructor function called branch. And what branch needs is, when you create a branch, it needs a start and an end. There's actually different ways of doing this, which you'll see later. And I'm just going to call, and I'm going to say this.start equals start, and this.end equals end. So the first thing I need to do now, start. So one of the things that often happens, which one of these is colored weirdly? Start is. So it looks like start is maybe a key word in JavaScript for something else. It shouldn't really matter here, but I'm just going to call this then beginning. Begin and end, just to kind of get away from that. Okay, so that's the branch, a branch object. And I know I could use like if some of you were like watching this being like, oh, maybe you should use a JavaScript object literal, and I could do that too, but I'm kind of using this constructor function because I'm going to add more to it, and you'll see hopefully later why that's kind of another way of doing it that could be useful. So I'm going to go back to the code, and right here, when I first call this branch function, what happened in the first program is I translate to the bottom, call the branch function, which draws a line. But instead, what I want to do is say, I'm going to make a variable called root, which is the root of the tree. And I'm going to say it's a new branch, which goes from where? The center of the screen, width divided by 2, to where? Like the, width divided by 2, height. Oh, so, so I'm doing stuff and just programming and like I got lost in my thoughts for a second. You know what I really need is, interestingly enough, let's go back and look at this. I said, oh, there's just 2 things involved in this branch, a beginning and an end. But what are those things? The beginning and the end, those things are points with an x and a y. And one way that I can store a point in P5.js is using a vector object, a P5 vector object, which is an object that has its own x and a y. So what I'm actually going to do is I'm going to say, I'm going to be very long-winded about this just to be quite explicit. I'm going to say a equals create vector, and I'm going to make a vector that's at the bottom of the window, width divided by 2, comma, height. And then I'm going to say b is a vector that is also in the middle, but not at the bottom. It's at the bottom minus this length, or 100, minus 100. And then I'm going to make a branch which goes from A to B. And then what I want to do, and I actually don't need this whole recursive function anymore. And oh, this should be in setup, by the way. And I'm going to get rid of this slider. We can come back to using that slider later. I guess I'm starting from scratch. And in draw, I'm going to say root.show. What I want to do is take that, oh, and this needs to be a global variable. So what I'm trying to demonstrate right now is I can make a single branch object, which is just the root of the tree, and I can display that root. And so I need a function called show. And so I'm going to add a function called show. And all that show does is stroke 255, draw a line from this.beginning.x, this.beginning.y, to this.end.x, this.end.y. So you're going to see here that a branch is just an object that has a beginning and an end point, and it's displayed as a line between those 2 points. So now if I come back to here and run this again, you can see there's our first branch. So we kind of double back. We're doing the same thing we did before, but in a different way. Okay, so let's think about now. Now here's the thing. What I need is for every branch to spawn 2 branch objects attached to it. How are we going to do that? So one thing I need actually is I'm going to have more than one branch, so I need an array. So I can, what the tree essentially is, I don't need this root anymore. I'm going to make a variable called tree, and tree is just an array. So it's an empty array, and then this root is the first thing that goes in the tree, and then, and I know that camera just went off while I'm in the middle of my typing. I'm going to put it back on. In the middle, what I'm going to do is then draw all of the trees. So now my structure is I have an empty array. I create the root of the tree. I put the root in the array, and then I display the array. And once again, I'm missing a curly bracket. Once again, I still have that one root. Now comes the time where I can attach to that root 2 more branches. So how can I do that? Well, one way that I could do that would be to add a function. This branch object, what if this branch object had a function within itself that knew where its end is and knew how to spawn 2 more branches from that end? So let's look at that. So I'm going to go back to this branch object, and I'm going to write a function called, and I'm actually just going to call it branch. I don't know if I have a naming conflict anywhere, but I'm going to write a function called branch. And what that function is going to do is it is going to create 2 additional branch objects attached to this branch object. So how do I do that? So I'm going to call the right branch is a new branch. I hear voices. Somebody might be coming. Who knows? There's something there. I don't know. I started thinking about West Side Story, one of my favorite musicals. There's definitely people here, and I lost my train of thought. Okay, I need to make a branch. So where does let's think about it. I need a diagram. I'm going to come over here. Okay, so if I erase this diagram, how am I doing this? I have this branch. This is begin. This is end. Now I need a new branch. So this new branch, its begin point is the previous end point. And then I need to calculate where is its new endpoint. And the way that I might do that is by rotating this line. So I'm going to need to use some trigonometry and math for that. Okay, we're going to get there. We're going to get there. Boy, this is hard to do without having just done it, just to do this from scratch on the fly. Okay, so let's see, new branch. So what I want to do is the new branch is going to start at the previous branch's end. And now I need to fill in where it ends. So how can I do that? Well, one thing I can do is I can make a vector that is the direction of this particular branch, right? What if I have a vector that points from here to there, a vector being an arrow that points from here to there. And the way that I can make that vector is by taking this point and subtracting this point. So I want to create a direction vector and say p5.vector.subtract. I want to subtract the end from the beginning. So now I have a vector that points from the bottom to the top of that branch. And one of the nice things about vectors is they actually have a rotate function built into them. So what if I were to rotate that vector by some angle, like 45 degrees or pi divided by 4? And then what if I were to create a new endpoint, new end, and I would say the new endpoint is where? It is add the endpoint of the previous vector with the direction. So in other words, what I'm saying is, let me come back over here again, is I now have this vector. Oh, wrong side of this pen. I now have this vector, okay? And then what I want to do is take this vector and rotate it by 45 degrees. And then I want to add this vector here. So this is the new endpoint. So this is the beginning, and this is the endpoint, and that's my branch. So now I can say the new branch goes from this dot end to the new end. That's to the right. Okay, so let's see how this works. So let me now go back to the main program, and I'm going to say new branch equals root.branch. Oh, what am I need to do something. So once I have that new branch, I need to return it. So I need to return it so that I can get it. And then what I can do is say tree index 1 equals new branch. So the 0 index of the array is the root, and then the next spot in the array is this new branch that came out of the root. Perfect. Look, now I have both of those. Now, I could probably cleverly create both of them in this function and then return both of them as an array and then add both of them. But I'm actually just going to call this function branch A. And then I'm going to do something kind of lazy and just make a function branch B and rotate the other direction. And, I'm just going to call this V or B. This is to the right, and this is to the left. So I'm just going to have two, again, a good programming exercise for you is like, how can you combine this into one function? Maybe you just pass in the angle. But just to be lazy and explicit for a second, I'm just going to have these duplicate functions. The only thing that's different is one is rotating to the right, one is rotating to the left. And I can go back to the main program, and I can say branch A. And I'm actually just going to combine this, say tree index 1 is branch A, and tree index 2 is root branch B. So now you can see this particular branch has two branches attached to it. Okay, things are going well now. Now, One thing that I want to do is, remember, I want to shrink the branches each time they're attached. So let's go back into this function here. This direction vector should also be multiplied by 0.67 in order to shrink it a little bit. And now you can see that it is now shrunk. So what I have now is I create a single branch object and it spawns 2 other branches. I need a mechanism for then having those 2 other branches spawn 2 more branches and 2 more branches. And maybe what I'll do is every time I click the mouse, I add 2 more branches. So let's figure out how we would do that. So let me go to Sketch and I'm going to take this out. And I'm just going to say function mouse pressed global and put this here. So in mouse press, I'm going to add those 2 branches. So now 2 branches, click the mouse. Ooh, root is not defined. So I'm going to say tree, the thing that's global is the array. Tree index 0, tree index 0. So I'm going to add those 2 branches. And now I'm going to click the mouse. 2 branches. There we go. Okay, so I'm getting somewhere. I'm getting somewhere. Now I have this ability to take an existing element of the array and add to it. So what I really want to do is not do it manually like this, but what I want to say is, hey, anything that's in the array, there are some number of branches in the array. What I want to do for everything that's in the array, I want to tree.add. So one way to add something to array is with the push function. I want to add tree index I dot branch A and tree index I branch B. So this is now an automatic way of saying whatever is in the array currently, go through everything in the array and add to the array with branches from the things that are in the array. Now, there are some problems here. Problem number 1 is, if I'm trying to loop through an array, like I'm looping, here's the beginning of the array, here's the end of the array, and I'm looping through it and I'm adding things to it. So as I'm going through the array is growing. I'm never going to get to the end. So one way to solve this would be to say, to actually start from the end of the array and go down to 0. This way, I can add things to the, like I'm going backwards through the array and new things can get added to the end that will then get ignored. So this should actually work, and I'm going to run this, and you can see I can click, and then I can click, and then I can click, and then I can click. So that's actually happening now. Each time I click, everything that's in the array gets 2 extra branches. But one thing that you might not be noticing here is that this particular root has been there every single cycle. So every time I go through that array, it gets 2 new branches. So there are multiple new branches being added over and over again in the same spot, which is very unnecessary. So one thing that I think could be useful to do is in the branch object, I could add a variable like, I'm going to call it grown or finished. I'll just call it finished. And it's going to, finished is going to be false. And in the branched function, you know, let's say I'm just going to say this dot finished equals true. So whenever, and you know what, maybe I'm going to actually, since I have this branch A and branch B, I'm just going to do it out here. So I'm going to say tree index I dot finished equals true. So what I'm going to do is every time a tree branches, I'm going to say finished is true. And then I want to make sure if tree index I dot finished, only if the tree is not finished, should I actually add those branches. So now, you can see every time I click the mouse, I'm adding branches. Now, this might not seem very exciting to you, because ultimately, all I have here is exactly what I had before. But the difference is, I actually have an array of objects, and all of those objects store their location dynamically where they are. So there's no reason why I couldn't do weird things like, in the branch function, in branch, I could say, I'm going to write a function called jitter. And I'm going to say this dot n dot x plus equal random -1, 1. This dot n dot y plus equal random -1, 1, 1. So one thing I'm going to do is I'm going to add this jitter function in draw. And I'm going to say tree show and tree index I dot jitter. So now if I run this, you can see, look at this, it's animating. And as I click, those are all animating and shaking and doing weird random things. So I'm not suggesting this is like a great result, because I don't know what I have here. I just have this random shaking weird tree. But you could imagine, what if you did something a bit more thoughtful? You were changing colors based on some logic, or maybe you were swaying with Perlin noise, or you applied some spring forces or a physics-based system to the tree. Boy, I really wanted somebody remind me someday to do a video where we take this tree and actually attach spring forces to all of it, so you can sort of like pull on it and it just goes, you know, it's all springy back into place or something. That's always a nice demonstration. So this opens up a lot of possibilities. It also opens up one last possibility that I want to show you in this particular video. So I'm going to turn off the jittering, and what I'm going to do is I am going to say, I'm going to keep track of a counter, and I'm going to just, every time I'm going to say count plus plus. And what I want to do is say if count equals 5. So if I've generated 5 generations of the tree, what I want to do is say for var I equals 0, I is less than tree.length, I plus plus. What I want to do is I'm going to make leaf objects. So I want to create an array called leaves. And then what I'm going to do is say, for all of those last branches, if and when I get to 5, any branch that hasn't branched is at the end, what I want to do is make a leaf. Where do I want to make that leaf? I want to make the leaf at that branch's end point. And you know what? I don't even need to say create vector, because it is a vector. Tree index I dot end dot copy. So I want to go and grab that end point of that branch and make a copy of it. And then I'm going to say leaves dot push that leaf. So now in draw, I can also loop through all of the leaves. And I can say, now I should make the leaves an object, the leaves. I'm going to make some purplish leaves. And I'm going to just make them circles. You can be more creative. Dot y. So we should get now, let's run this. 0, wait, 1, 2, 3, 4, 5. So you see, so let's do a couple things. One is, let's make that angle. Where did I decide what the angle is? The angle is right here. It's kind of like hard-coded in. So this, by the way, would be nice to make a variable. Maybe it could be slightly random. That could be the thing that's changing. But, oh, and I did something interesting. So for some reason, I'm going a different angle to each side, which is kind of nice. And let's go in Sketch. Let's actually go up to 6 levels. And let's say no stroke for the leaves and give it some alpha also. So you can see I now have little leaves at the end of the tree. And what's exciting about this is they aren't just circles on the screen. Those are all vector objects. And what I could actually do, if you go look at any of my other Nature of Code tutorials, I could treat those as particles that would fall with the wind or something like that. And just to sort of show very, very briefly, what I could do right now is I could move all the leaves by some random amount in the y direction. So once I get up to 6, you can see they're falling. Now again, I have made a really trivial, whoops. This is a trivial result. You know, I don't like necessarily that doesn't look like a very nice, glowing, beautiful physics movement, but you, in thinking about color and thinking about motion, all sorts of possibilities, you could have the branches be swaying, you could have a gust of wind, some of the leaves fall, some don't. What if you have a program where you shake the tree and the leaves fall off and they don't all fall off at the same time? All of the possibilities are now open to you because the fractal wasn't drawn through a single recursive function, but rather was drawn as a set of objects with position vectors. So all of those things could be manipulated after the fact. thanks for watching this video. If you make something with this, please let me know, and I'll see you in the next one. Okay. Was that helpful? Did that make sense? That was very long. I think that was probably about 25 minutes. Actually, I have no idea. If you have some questions, now I'm going to take a moment while I kind of get my thoughts in order to get to the next. The next thing I want to do is an L system. So I'm going to get my thoughts in order and get set up to do the L system. And I'll check the chat to see if people have questions. I'm just checking Twitter for no reason and seeing if all the streams are still working. Unfortunately, I didn't get Twitch today. I apologize for that. Okay, just checking. Everything seems to be good. The other thing that I didn't mention it, but a good exercise would be to actually animate the branches also. So instead of just appearing one at one, have them animate. That's a good thing to try to do. Okay, so what I want to do right now is I'm going to open up one of my L system examples from, there's a new version of processing. Let me go and download that, just so I'm in the most recent. And I need the Mac version. So I'm going to set that to downloading. That'll be done in just a second. So I'm going to go and open up, I have an existing from Nature of Code L system example. And I want to go take a look at that and just kind of like refresh my mind about the code and look up the Wikipedia page on L systems and kind of like figure it out a little bit. And then I'll start and do a tutorial where we make the L system from scratch. Okay. I don't know why I'm feeling all. Ooh, someone in the chat is asking, Dan, would you think it can be possible to create a user interactive sketch using sockets and node.js? I have a tutorial series that does exactly just that. So I think if you search on YouTube for a playlist, it's like web sockets and node or something like that. I have a tutorial series that makes a shared canvas. Okay, so processing 3.1.1 has now downloaded. You know what I need is a thermometer in this room. I'm wondering how. Is processing open? I need to make sure it's not. And I'm going to just copy this to the desktop. I hear voices. I kind of recognize the voice too, but I can't figure out who it is. It's a voice that I recognize. Somebody is here at the School for Poetic Computation in the other room. Okay, so I am. So I'm going to contribute an example. Sorry, everybody. This is just, I'm taking a moment here. Chapter 8, simple L system, L system. So let's look at this one. And let's see here. Yeah, so this is the one that I want to do, because we'll get this nice tree. And this comes from the Computational Beauty of Nature book. I mean, it doesn't come from that. That's where I found the implementation. But, you know, L systems, and I guess I should mention something about this. So let's look up Lindenmayer system. So let's look at the history. Okay, Aristide, 1968. Somebody tell me if I'm pronouncing this correctly. Aristide. So Aristide is or was, I'm not sure. Let's look up. Is he still he or she? I assume a he, I believe, by the name. 1989. Okay, no longer still alive. A Hungarian biologist, and you can see here various examples, and so we could do this one. I'm trying to think of. Yeah, maybe what I'll do is start with this and only just do the text. And once I do that, I will go and do not this one, maybe like this one, fractal plant, or the other one that I have. There's all, sorry, this, I can't tell if it's people here or upstairs. Can you guys hear the voices? Okay. Okay, so I'm going to scroll down here. And then, okay, so what I want to get is this particular. So I'm going to do this in a simpler way than it's in this example, but I'm going to save this in like a file somewhere. Sorry, I'm getting myself ready. So I just want to save this one. Okay. And let me get the other one that I'll implement first. Okay. Great. Then okay, so these are the two L systems that I'll implement. And what I'm going to do in this tutorial is first just talk about what an L system is, the theory behind it, why it exists, how it works. Then I'll make a P5 sketch that does the sentence writing and rewriting, and I'll just have that happen as text in the browser. And once that's done, then I'll use this and have the sentences be interpreted by a Turtle graphics engine, which will draw stuff to the screen. Right? Okay, everything's going to be fine. Okay. I don't know what's going on. I shouldn't look at the chat anymore because it's distracting me. But if you have questions, I'm peeking at it. Okay. So now let me just open this up. So this is my visual reference. So I have browser, L system page. I think I need to start with a completely blank sketch. So where am I? Desktop, algorithmic botany. Let's start with this one. And I'm going to call this now L system. And I'm going to open this with Atom. Where's Atom? Here it is. Do I have all the other ones still open? I'm going to close them. Okay, so this now. And function draw. Okay. Okay, so I think I am ready to go. Here it is. Okay. Okay, let me check. Oh, I see a question. Is there any physics library in JS that you recommend using alongside with P5? No. I mean, I'll tell you what I have used. You know, I used Box2D with processing. So with my nature of code examples, I have a port of all those using a JS version of Box2D. But I don't necessarily recommend it because it's kind of confusing to use, but it's useful if you want to use Box2D. There's also something called Toxic Libs, which is originally was a processing library, and someone made a JavaScript version of it, toxiclibs.js. It's actually quite wonderful for Spring-based systems, and I do have some tutorials about this in like very old videos from several years ago that are in my YouTube channel that you could look at. Otherwise, I'd be curious for other JavaScript physics engines that people have experience with and have liked, and I would be glad to investigate those in connection with P5 in some future video tutorials. Okay, so I'm going to cycle these cameras, and then I am going to clean this whiteboard in order to have it fresh. I want to get to the, oh, my watch. My watch battery died. I have a Pebble watch. I'm trying to decide if I should get the next Pebble. Next generation that's on Kickstarter now. I don't know why I'm buzz marketing Pebble watches. I like Pebble watches. Okay, that's all clear. I wanted to see what time it was. It is 3 o'clock. I think we're doing reasonably well. I feel like I really want to get to the space colonization because, you know, we should all colonize space. Why not? And that was the new thing. But it's just water. The spray is just water. It says all-purpose cleaner, but I mean, it might have been all-purpose cleaner at one point, so it might have that. I wouldn't drink this, but just using water to clean the whiteboard. So it just, this, I don't know, I don't have a good eraser. I'm wasting these paper towels. I need a better system. Oh, the camera moved a little bit. Which camera? Oh yeah, I see that. You know, it doesn't bother me too much, but I'll fix it. Perfectly balanced. There we go. Thanks for pointing that out. Okay, time for L systems. All right, I fixed it. Now, here I am, coding challenge, L systems, P5JS. Aristid. Aristid? Aristid? Who knows how to pronounce that? Somebody will tell me. Okay. I'm just giving myself a minute to think. People are telling me my pronunciation was good, but I pronounced it a few different ways. Maybe the first way. Okay. You can see more of my bald spot now that my hair is shorter. I just feel the need to get that out there. Okay. All right, here we go. It's a closed A, like ah. Aristed. I was going to say awisted, but aristed. Okay, thank you. Okay, here we go. Aristed. Okay, here we go. The chat is like, aristed. Okay, aristed. Okay, what I want you guys to do for me in the chat is I have it if something goes wrong audio-wise or video-wise, flood the chat with like crazy emoticons, okay? And I'll notice. But I'm gonna not look at the comments while I'm doing this particular session. Okay, here we go, L systems. Hello, welcome to another coding challenge. This one is all about something called an L system. So in this video, I'm going to, from scratch, program and implement, make this tree appear on the screen with something called an L system. This is a bit of a follow-up to 2 previous videos I made about fractal trees, but this one can also stand alone. You can watch it without watching those other ones. Now, so what is an L system? An L system, first of all, L stands for Lindenmayer, for Aristid. Oh, Aristid. Let me just start this whole thing over. I'm really in my own head about Aristed. Okay, anyway. Okay, here we go. Hello, welcome to another coding challenge. This is a coding challenge all about L systems. I'm going to make this beautiful tree. I think it's a little beautiful, but you will hopefully make an even more beautiful one after watching this video. But I'm going to make this tree appear in the browser using HTML, using JavaScript. So what do I want to do here? I want to define what an L system is, look at how the algorithm works, and then build the code for rendering an L system from scratch. Okay, so what is an L system? The L stands for Lindenmayer, for Aristid Lindenmayer, a Hungarian botanist who developed this algorithm for modeling cellular growth. So you can read more about L systems. I've got the sort of Wikipedia page here as a reference. But what I'm going to do is just kind of define for you the guts of it, the sort of like the actual terminology associated with an L system. So an L system is actually all text-based. We're going to use it to generate graphics, but at its core, it's just text-based. And it involves a few things. It involves an alphabet. For example, my alphabet might be the letters A or B. These are also sometimes known as variables. It involves an axiom, meaning what is the beginning of our L system. Our L system begins with an axiom. For example, an axiom could be A. And then it involves a set of rules, meaning something like A becomes A, B, and B. Well, hold on, let me look. I have actually the one that I want to start with, which is sort of A becomes A, B, and B becomes A. Okay, so look at that. I just wanted to use, since, and B becomes A. I don't know if the camera switched while I was doing that, but so and it has a set of rules. So what does this mean? So an L system is a recursive way of generating sentences over and over again using string replacement. So this is the set of elements in the L system, and we start with the axiom A, and this is generation 0, and in generation 1, we apply these rules to it. A becomes AB. A becomes AB. And now we do this again. I have generation 2. AB, A becomes AB, B becomes A. And generation 3, A becomes, I'll stop doing this eventually, A becomes AB, B becomes A, and A becomes AB. Hopefully I did this right. Manually as a human being kind of doing this string replacement, I could easily get it wrong or it could take me forever, be very tedious. This is the kind of thing a computer is perfectly, beautifully well suited to do. And what we have here is with this type of system, these kind of recursive fractal-like structures appear in the text, the resulting text itself. So it's up to you to say, aha, I have this system, I've designed it, I have an alphabet, I have an axiom, I have a set of rules. I should write rules here. And now I've generated these sentences. What do I do with the sentence? It could be you read it as poetry. A, B, A, B. Or perhaps you use it to be a song. A, B, or with rhythm. Or you tie it to graphics. You know, this means a dot, this means a square. And you draw a pattern on the screen. So you could imagine there's a lot of ways you could interpret the L system. And what I'm going to do is first program just this string replacement structure, and then I'm going to show you how you can use a certain kind of alphabet to indicate things like draw a line forward, turn right, turn left, and create all sorts of patterns, in particular plant-like patterns on the screen. Okay, here we go. Coming back over here. So we've got this down now, and let's start writing the code for it. So this is the one I want to do first, and I called it variables here. So I'm going to go I've got a JavaScript. I've got a JavaScript file here. I'm working in the browser using the P5.js JavaScript framework, and I'm going to just put this here at the top and comment it out. So what do I want to do? I want to start with an axiom, and I'm going to say that axiom is A. Now, I also need to have some rules. So what would be a good way of creating a rule? In JavaScript, a way I could do that is I could make it a JavaScript object. Like I could say A, whenever I see A, it becomes AB. And I could say that's rule 1. And then I could say rule 2 is B becomes A. So now again, this is a highly manual way of doing this. And A and B are my own made up things. And oh, it's a little bit confusing that I did that because the alphabet. So maybe it's fine. I'll use it. Once I get to the next example, it'll be a little less weird looking. But the point is A becomes B. So I'm looking for A, and whenever I see A, I substitute it with B. So now, I'm going to write a function and call it generate. And what I'm going to do is in setup, I'm going to say no canvas, and I'm going to use the p5, and I don't need draw right now. I'm going to use the p5 function called createP, which creates a paragraph element in the page. Pause. This will get edited out. I don't know. I'm really having an issue where I just constantly feel like I need to blow my nose, and it's distracting me. So I'm gonna, when I make this a standalone video later, I should have muted my microphone before I did that. Okay. Back. Okay, so I'm using createP, and I want to say createP axiom. And I'm going to run this now in the browser over here. And we can see, there we go. I have the letter A appearing. So my first axiom has appeared. So now what I need to do in generate is what I want to say is I need to look at every letter in the current sentence and substitute using the rules. So I'm going to say for int I equals 0, I is less than axiom.length I plus plus. And you know what? I want to have a new variable, and I'm going to call it sentence. And sentence is going to start with the axiom. So I'm going to say sentence.length I plus plus. Then I'm going to say the current character equals sentence.char at I. So what I'm doing is I'm looking at, this is something you can do with strings in JavaScript. I can look at each character one by one and pull it out. And I can say here, if current equals rule1.a, then, and now what do I also need? I need next sentence, which is an empty string. So what I need to do is build up the next sentence. If current equals the A part of a rule, then next sentence should get B. So if it equals A, substitute B in. Else, if current equals rule1B, next sentence plus equal rule2, A. So, right, if it matches A from rule 1, substitute in B from rule 1. If it matches A from rule 2, substitute in B from rule 2. Otherwise, just keep it. So there are cases where you have a character and it doesn't match any of the rules. In that case, you just keep that same character. So keep current in. So if current is A, is rule 1's A, put in rule 1's B. If current is rule 2's A, put in rule 2's B. If it's not any of the rules, just keep current. And then at the end of this, the sentence should be now the actual current sentence is now the next sentence. So I'm gonna say createP sentence. So now, so when do I generate? So let's make a button. Var button equals create button, generate. So create button is a function that's in the P5 DOM library, and I can attach an event to it, and that event is generate. So whenever I press the mouse on that button, I want to call that generate function. I just want to go something, I want to remove some of this unnecessary styling. And now I'm going to refresh this page. Oops. So sketch.js line 20, I have some sort of error. Oh, I used int. It should be var. And I'm going to, okay. So now you can see here, I have this generate button and I have the axiom there. And I see AB, ABA, ABA, AB. And you can see, hopefully this is right. I'm going to generate a bunch of times. And you can see I'm generating sentence after sentence here. So this is the idea. So I could do this forever and ever and ever. I'm sort of curious why it's not like word wrapping, but I'm sure that's just some sort of CSS styling that I could fix to make it wrap to the next line or whatever. Anyway, let's not worry about that. So you see that this is the idea that works. All I need to do is create an algorithm for generating for starting with an axiom, having a set of rules, and iterating and doing string replacement. Now, I did some kind of sloppy things with that just to sort of like make it work. It would make much more sense for this to be an array and for me to say something like rules index 0 equals this. And so I just want to, and rules index 1. So it makes much more sense for me to have the rules be in an array because there's no reason for me to be checking both of those as separate else if statements when I could really just say for I equals 0, I is less than rules.length I plus plus, and I can't use I because I already used I, so this has to be j. So what I want to do is instead of checking each rule individually, because what if an else system I have eventually has like 10 different rules? This will become a mess. So in that sense, I can say if current equals whichever rules index j dot a, then next sentence should equal rules index j dot b. And then what I can do is I can put a break here. So I can sort of get out of the loop as soon as it, because more than one rule can't be true, so I can get out of that. And then what I need to do though, however, is I need to figure out a way of adding if none of the rules are met, are found, then keep that current character. So one way I can do that is I can say found is false, and if I found one of the rules, found is true, and then at the end, once I've gone through all of the rules, I can say if not found, next sentence plus equals current. So this would make sure. So this should be identical to what I had before, and if I run this, we should see the same exact result. Now, we aren't really sure. One thing I should do to make sure this is really working is I should change this to have this actually become like ABC to make sure the C's continue through there, which they do. So you can see this is still working. So now I have a bit more of a flexible system by which I could just create an array of rules. It doesn't matter how many rules, it'll still work. Okay, now we've got the basic mechanics of the else system down. The next thing I need to do is do something more to draw from it. So what I want to show you is I want to now use this particular else system. So these are the letters of the alphabet for this else system. F plus minus open bracket, close bracket. We start with F, and this is the rule. It seems like a crazy rule, but it's actually going to do something quite interesting. So what I want to do is here, I want to start with F, and actually I only have one rule. So this is actually a much simpler scenario, which F becomes this. And now I should be able to run this. Start with F, and you can see, now it's wrapping, but you can see this is what I get. Even just in the third generation, this is what I get. So this looks totally insane, but this is actually incredible. These are entire instructions for growing this elaborately complex plant-like shape. And this is really magic, and you can get the computational beauty of nature or the algorithmic beauty of plants. There's all these books and resources where you can find countless numbers of these kinds of else systems, or you can invent your own to create these patterns. But let's make this one happen. So all that we've done so far is we've only made a program that renders the text to the screen. Now what I need to do is have a program that reads the text and draws to the window. So how do I do that? So I'm going to go back, and I'm going to get rid of no canvas, and I'm going to say create canvas 400, 400, and I'm going to say background 51. So let's make sure there's now a canvas appearing. Great, this is still working, but now what I'm going to see is every time I hit generate, I want to read this text and draw to the screen based on it. Okay, so let's do that. Let's now write a function, and I'm going to call this function turtle. So I'm calling it turtle is because I am going to interpret this particular text like a turtle graphics engine. what is turtle graphics? So the concept of a turtle comes from an old programming language called Logo, where you could write code to move to instruct a turtle how to move around the screen. And as the turtle is moving around the screen, the turtle is drawing lines. So you could say things like F means move forward. So move forward and draw a line. Plus means turn right. Minus means turn left. And what's especially sophisticated about the turtle graphics engine that we're about to implement is that these brackets mean save where you were. So you could be a turtle moving around the screen. At any point you could say save and you could keep moving, and then you could say restore and go back to there and move from there. And that's going to create a lot of sophisticated possibilities. So what I need now is in the code is to write a loop and just go through every single character in that sentence. And I'm going to say current again equals sentence car at I. So now what do I need to do? If current equals F, I need to draw a line. 0, 0, 0, negative length. So this is somewhat arbitrary, but I'm going to start with the default mechanic that I want to have this be my original position, and I want to start drawing a line up. So from 0, 0 up to there. Then I want to say else if current equals plus. Then I want to say rotate by, I'm going to try pi divided by 6, which I don't think is right, but I'll just start with that. Else if current equals minus, rotate pi divided by 6 in the negative direction. Else if current equals bracket, open bracket, push. Push is the function in P5 which is save the transformation state. So I'm going to move around with translate and rotate, and push is going to be save. Else if current equals close bracket, I'm going to say pop. So now I'm going to pop. So this is everything. Like, this is the thing. I don't even have to really think much about it. Like, all of the magic is happening in this L system itself. I just have to write the instructions to know what to do. But I did miss something. So one of the things that I have to do is when I draw this line, I then have to translate to move to the end of the line. So in addition to drawing the line, and we come back over here, I need to say translate 0, negative length. So I need to move to the end of the line so that I can either draw the next line or rotate from there and that sort of thing. So, and then we need this to be a variable. I'm going to say length equals 100. So what I want to do now is, let me find, there's so much stuff going on here. What I want to do is whenever I generate, I want to also call turtle. So I'm going to call turtle once in setup, just so the axiom is drawn. And then whenever after I finish generating, I want to call turtle again. Okay, so here we go. So I don't know why I don't see the line. Okay, so let's see if we can figure this out. Turtle, so first of all, let's draw the background again, and then do stroke 255. Oh, I know why we don't see anything. So where is the line being drawn? It's being drawn from 0, 0 up. So I need to actually at the beginning make sure 0, 0 is positioned at the bottom of the window. So the very first thing I need to do in setup before, or anytime before I call turtle, is I need to say translate to the middle of the screen and the bottom of the screen. And whoops. There we go. So now you see F. The sentence is currently only F. So all I have is that one line. Now look at this. Let me do generate. And now we have FF plus save plus F minus F, restore, et cetera, et cetera. Let's look at this. Now, it went crazily off the screen. Now, why did that happen? Something weird is going on here. So let's investigate this. I don't have a draw function, so I wonder if something weird is happening. Okay, hold on. Why did it go over to the right? Because it should just go up, up. Let me do something here just to see if something... No. Whoops, whoops. Whoa, craziness is happening. Hold on. I wonder if I'm using an old version of P5. Timeout. I got to fix this problem. This will March 4th, 2016. Oh, this is, I think, did I not notice that I was like kind of old, an old version of P5 of library? Whoops. Okay, I'm going to fix this now. This will get edited out of this particular video. I thought, no, I started from what I had yesterday. So, P5. So this shouldn't matter. Replace, replace, replace. Is that the March 4th cannot be the most recent version. I wonder if May 2nd, version 5. Why is that not, why is this download not the most recent version? Someone, that seems weird. I was curious if anyone could check if you download and use this empty example, are the libraries not actually the right ones in that libraries folder, or am I just going crazy? So now I'm in here. Replace, replace, replace. I'm losing my mind here. Whoops. March 4th. Why do I keep getting March 4th? Okay, I've done something crazy. Let me go to, I must just not be paying attention to what I'm doing. And go to releases. I'm going to get these individually. So P5.js, P5dom.js. I'm not using sound, but I'm going to download it anyway. Those are version 5. There was a weird bug with translate at one point. So that's what I think I just ran into. Where am I? Desktop, desktop, algorithmic botany, L system, libraries, delete these. Yeah, now I have version 5. Yeah, okay. Let's see if that fixes the issue that I'm having. I wonder if the no draw is kind of an issue. Or, okay, I'm going to figure this out. So one thing I want to do is let me just make sure this is working. I want to make sure translate is doing what I want it to do. So I should see a red circle, a green circle. Yeah, so why, that green circle should always be there. Why is it really, I shouldn't need, so one thing I could do is just call turtle every time in draw instead of this. Yeah, what did I miss? Background. It should start over each time, finish the sentence, and do it again. So y currently, I didn't say y currently, translate with divided by 2, draw that line. So let's see, print line. Yeah, that's running over and over again. Did I stroke 255? Why? This is the problem. This is a problem, by the way, that was fixed in P5. Like, I don't know what's going on that I'm seeing this problem again, but yeah. So I shouldn't have to do that. This was an old bug, and it got fixed, and I don't know why I'm seeing it again, where everything should reset at the beginning. Yeah. But you shouldn't have to do that. This should happen by definition. Well, I'm just going to leave it in there. So this should happen by definition, but I'm going to investigate this later. Yeah, that's what I expected to see. So weird. Okay. So I'm going to come back to this video in a second. I'm going to get rid of this ellipse. So one thing that is missing here is that the length should shrink also each generation. So, and I believe the angle is actually 25. I'm going to, well, since I'm taking this break, so let me just look at my processing code to see. Let me just see what I did. Yeah, I did it in processing too, because I used redraw by 0.5, and then the angle is that I used is 25 degrees. Okay. Okay. All right. Hold on. I guess I've been doing this one for a half an hour. Okay. So I'm going to come back. Okay. So this will come, the video, when I make this a standalone video, it will come back somehow. Okay. That's weird. So I'm going to have to, I really have to investigate that. I'm losing my mind here. But yeah, it should, yeah, because I haven't done draw, but I also tried draw. I'll look at it later. But yeah, I think because I'm not doing it in draw, I need to call reset matrix. I'll mention that. Okay. Okay. Edit now back in. Okay, I don't need to do the okay, back. Sorry for a technical difficulty. I've added in reset matrix just because I'm not doing stuff in draw. That guarantees that each time the turtle function is called, 0, 0, and all the rotations and translations are restored. So you can see now, if I run this code, F means just only draw forward, generate. Now I'm actually interpreting this, which means draw forward, turn right, draw forward, save, turn, oh no, wait, turn, actually that turned left, draw forward, save. I can't figure it out. But you could probably figure it out. Why can't I figure that out? Oh, timeout, this is not the edit point. I got to come back and start over. I'm losing my mind, right? Draw forward, go forward, turn right. Save. Turn right, save. Turn right again. Go forward, turn left, draw forward, turn. Okay, I got it. Coming back. Okay. Back after a technical problem, I added in reset matrix in this turtle function because I'm not using the draw loop. This guarantees that I'll always start my translations and rotations over again each time I'm about to draw this L system. Does that fix this sort of issue just with the way that I'm doing it right now? So now you'll see, if I hit refresh, you can see that I'm drawing F. When the sentence is only F, I just draw one single line forward. And now when the sentence is FF plus save plus F, then I'm saying go forward, turn right, save, turn right again, go forward, turn left, go forward, turn left, go forward, then come back, then turn left. So you can see this is a great exercise for you to do on a Saturday afternoon outside in the park. Copy down one of these sentences and get out graph paper and try to be the L system. But you can see here, now all I got to do is hit generate again, and something much more complex is happening. But I sort of have lost the picture. I don't see what's going on. So a couple things are missing. One is I picked a random angle to rotate by, pi divided by 6, which isn't actually the angle meant to be used with this particular L system. So let me first fix that. So I'm going to go into the code, and I'm going to make a variable called angle. And in setup, I'm just going to say angle equals radians 25. So 25 degrees, I believe, is the angle meant to be used with this. And then here, I can just say rotate instead of pi divided 6 by angle and negative angle. So now I have a variable I could change. So let's run this again. I guess maybe pi divided 6, 25, and I'm losing my mind. Looks the same. I'm really losing my mind. But regardless of that, the issue, I'm going to have to check that in a second. The issue is that with more and more generations, I actually want to shrink the length that I'm drawing all this stuff. So it would make sense here in the generate function to each time I generate, I could say length times equals 0.5. So now you can see that's how I start, then's next, then's next, then's next. So I had it right. Maybe pi divided by 6 was right all along. I'm going to do one more generation. And you can see how intricate this becomes. And what I might like to do is just give this a tiny bit of alpha. So we can zoom in on it here and generate, 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 generate. And so at a certain point, it's so much for it to draw, but you can see I've got this full structure, beautiful structure now. Just try to imagine drawing this through some other mechanism. So I encourage you to play around with this, go investigate, find other else systems, plug them into this example, see what kinds of patterns you get. The other thing that you might think about is if you watched one of my previous videos about how to turn a fractal tree into a whole set of branch objects that you could apply physics to, you can also do the same thing with this particular example. And if people are interested, at some point I could release an example that does that or make another video that converts this into that. So thanks for watching this L system video. Hope you go forth and make some L systems and let me know how it goes. Okay, do it in 3D. Everybody wants 3D. I'm getting to 3D. I'm gonna do, it's 3:40. This has now been a 2-hour live stream, so I need a minute to get my head wrapped around. I missed the editor war. I'm glad I missed the editor war. And the last thing I want to do, I don't know why I'm all my nose is running, feel all itchy. Might be the heat. Or some rare disease, or maybe it's fleas. I have all the West Side Story songs stuck in my head today. Ooh, it's very hot in here. I should start singing some Cole Porter. Okay, so I'm going to put this aside right now. And okay, so here is the thing that I want to look at now. So, save the hardest for the last, of course. Space colonization. Look at this. Not this space colonization. Space colonization algorithm. There we go. So this is another algorithm that I want to do and implement and see how it goes. People are asking interesting questions. All right, what's on my, so I'll pause and answer a few questions. On my t-shirt, this is a Processing Foundation t-shirt. It says people doing strange things with software, which is an old little ditty from the processing history. Just wondering what education do you yourself have? Did you study CS? I actually did not study computer science. I mean, I guess I studied computer science, but I never took I did take one computer science course actually, but I teach at a program called ITP, which is at Tisch School of the Arts at New York University. And I also went to this program, and that's really where I learned programming and creative coding and got involved with processing and that sort of thing. And that was between 2001 and 2003. Okay. Okay, so let me see here. We're going to get to this algorithm. The first thing I need to do is go and find, I did a version of it earlier today, which I just want to grab to look at. And where can I get that? Here, documents, oh wait, no. It would be probably in, where did I put it? So sorry everybody, this is going to take me a second to find Space Colonizer. Here it is. I'm going to copy this, and I'm going to put this on the desktop here. So I tried working on this earlier today. So this is a completely different algorithm. So I just running it through real quickly. So I want to go through, and I think there might be some flaws in the way that I've built it, but I want to go through this particular space colonization algorithm, how it works, and write the code for it, and then do it in 3D. Okay, so let me see here. First thing I need to do is erase this whiteboard again. So this is an algorithm. The next one I'm going to do is an algorithm that I absolutely do not have a video tutorial about before. I have actually never looked at it until this morning. And I read a few different web pages that document how the algorithm works and what it's for. And then I tried to write a processing sketch that implemented it. And I feel like I haven't 100% gotten it right. So maybe through this process of doing this live in a live stream, it will somehow work itself out. OK. So let me find some resources, close some stuff out. So I want to open up some links. So the main link that I found, ooh, look at this. Ooh, someone made this. Let's look at this. Oh, look at that. Oh, I like this. Starting in the center, that's clever. And making it, doing the thickness, that's really nice. This is from Jeffrey Pons from 3 years ago. I just found this now. I would like to look at this more. Tree generator, what I'm looking for, okay, this was a very useful page that I used that kind of goes through the algorithm. So, and also shows it in 3D. Ooh, this is nice. So this shows it in 3D, which I would like to attempt. I should probably do this. First, ooh, I like this. Okay, is it going to do it? Let's see it grow. Okay, so that's pretty interesting to see. Anyway, so you can see, so this is a nice page. But this comes originally, there's a paper. Whoops, no, I want to keep this one. Where is that one? That's Sea of Memes, yeah. What I want to, this is it. I want to find the original paper. This is it, I think. Yeah. So to properly credit. So this is the original paper that I also read through, and I think this is a good reference page. Okay. So let me, someone is noting in the chat that you're watching a live stream of somebody on YouTube watching YouTube videos. I could watch a video, if you really want me to be correct, I could watch a video of myself to try to figure out. So let me try to describe to you guys this algorithm, and I'm probably then going to do it again, because I need to sort of refresh my memory here. So the idea, and how I want to check my audio levels, actually. They're fine. Excuse me. It's hard to do this for a long period of time. The idea is that this is like the inverse of the other types of tree generation algorithms. Instead of starting from the bottom of a tree and growing the tree out, you actually start from all the endpoints of the tree. And then you still go back to the bottom and kind of grow to be attracted to them. But I definitely need to get a fan. Hold on. You guys like tolerate a, let's take let's take a 1 minute break. 2 minute break. Talk amongst yourselves. I'm going to see if I can find a fan. It's like, it's got to be like 100 degrees in this room right now. And then also, I'm going to be right back. I'm going to mute myself. So I don't have my music to play yet, but I will someday. Success, I have a fan. Okay. Now we'll see if this causes any audio problems in terms of making noise. I'm going to plug this in. I don't know if you can see me. I'm plugging in a fan. It's nice and quiet, this fan, I think. It's very low. Is there a... There must be an option to... Oh, here it is. All right. Can you hear that fan? You probably can. I'll turn it down a little bit. Let me know. Can you hear the fan? I'm standing over here, and the fan's on very high. Can you hear it? Please let me know in the chat. I need a... Yes, you can hear the fan. Okay, I'm going to turn it down. I'm assuming that now it's better now. Is it? What about now? Can you hear it now? Okay. Okay. Yeah, I can actually feel the air coming in, and it's like a tremendous relief. So this is going to help. Okay. So here we go. We're going to work on this space colonization algorithm. So let me come back over here. And so the way that this works is what you do is you have some sort of volume. So imagine this is the volume. And then what you do is you create a whole set of random points inside this volume. And these random points are known as leaves. So these are like the leaves that would be on the end of a tree. And you have a minimum distance. You have two important variables, minimum distance and maximum distance. I'm sure there are other variables. And what you do is you start down here. And where like the trunk would be. And you start creating, so I have a branch that's moving up. It moves up to here. It always moves by, there's some fixed length. The fan, I can feel the air over here. You can't see me anymore, but I can't feel it over here. That's fine. I'm usually by the computer more. Okay, so it moves, so you move up to here. So I'm going to keep moving up. This is the thing you do at the beginning. Until you are the end of the branch is sufficiently close to at least one of these leaves. And then what you do, sorry, I'm thinking this through, is you're no longer, so you get this trunk going. So the trunk is like its own special thing. I'm kind of going to gloss that over. So I'm going to just say for simplicity, you draw the trunk. And then you're starting here. And you have this idea of a branch going in a particular direction. Now, what the leaves essentially become are like attraction points. So what you do is you iterate over every single leaf. And any leaf that is less than the minimum distance to an existing branch. So let's just pretend for a second like this is already like kind of done some branching. So let's say you're currently you're iterating through every single leaf. If a leaf is sufficiently close, like if there's a leaf here and it's within a minimum distance, you delete it, meaning it's gone. Otherwise, you try to find the closest branch to that leaf. So let's say this is a particular leaf, and this is the closest branch. So essentially what you then do is calculate a vector that's pointing from this particular branch, end of that branch, to that leaf, and then that vector is like a force that pushes the branch toward it. So the idea being that, I wonder if I can make is that if you kind of have this branch growing, it's kind of going to get it's going here, and then it kind of goes here, then it kind of goes here. Oh, then this gets deleted, and then maybe a branch gets pulled that way. And you kind of keep adding branches so it can go in multiple directions. What did I miss here? I missed something. Let me go look at my code. I'm thinking this through. So let me go back to this code. So in other words, what I'm doing is for every single leaf, I look for the closest branch. Okay? So for all the branches, I'm looking for, and I'm going to do this again and explain it as I do it, but I'm looking at a vector between each leaf and each branch. So the branch position is really its end position. And I find that distance. And if it's less than that minimum distance, then the leaf is finished. If it's greater than that maximum distance, then it doesn't count. Otherwise, I'm looking for the closest branch. And once I find the closest branch, then I push it towards. When do I add branches? And then I go through all the branches. Oh, yes. And I increase the count. So every time a branch actually, so these things are just moving, and whenever it gets sufficiently close, it gets pulled in that way and also spawns a new branch. Is anybody still watching this? Is this making sense at all? I see a bunch of people have to leave in the chat. Let me know if this is making sense, because I'm going to explain this again. Let's look at this particular page, which explains it kind of nicely. Okay. So the idea here is that this is a nice diagram. That you can see all these dots. These are all these branches getting attached. And for each branch, it kind of looks and tries to find something close, and it can get pulled in that direction. And then also, and then it adds a new branch. So the branches the branches, once they're there, are fixed. It's really a segment. The word, I think what I'm missing here, I get it now. What I'm missing here is that the idea is a segment. So you get pulled in that direction, and then you add a new segment. And that segment continues to get pulled in that direction. You add a new segment. That makes sense. The question I have is what causes this to happen? I think what causes this to happen is that there are multiple branches being layered in the same spot. And so some will go off to the right, and then leaves will get removed, and that will cause others to go off to the left. And I think that a lot of these algorithms then use the more branches are layered in a specific spot, the thicker it is, I think. People are just chatting in the chat. I don't know if anyone's actually listening to me. So that helps me understand it a little bit. So this is the algorithm. And I kind of did that, explained that. As you see in figure 3, the attraction of nearby leaves pulls out branch segments from the existing branches. A leaf drops out when it has been reached. Eventually, all the leaves are reached, and you no longer add branch segments. There must still be leaves if you place them. There might still be leaves if you place them too far away to be seen by any branch, more than max distance, but you won't be adding branches. It says, unfortunately, there's one pathological case in this algorithm. If you have two leaves on opposite side of a branch point, the average direction will not be toward either leaf. Then the branch grows away from the leaves. On the next iteration, the two leaves will still be closer to the origin point, generate the same segment again, producing an infinite loop. I haven't had that happen to me yet. And then rendering. To get realistic looking branch side, you can pass over the branch segments and increase their size as they join. That makes sense. So I need to investigate that at some point. So this is why I want to do this in 3D to see how that works. So let me run this again. So I think this is right. I think I'm getting this sort of funny behavior just because I seeded it with a square. And I think if I seeded it with a circle, and also, I don't get why it stopped, but I guess I don't have enough branches getting close enough. Like, for example, if I made the minimum distance less, yeah, I'm not going to worry about this too much. It's kind of interesting. So I'm playing around with this, and that doesn't get me anything for some reason. Yeah, okay, I don't know what's going on. So maybe I'm gonna, oh, there we go. I'm gonna program this again from scratch. I think I missed something. And this kind of looks right. I think there's a bug in my code, because I don't see why this maximum distance, I think I'm measuring from the wrong place. Am I making copies of the vectors always? Oh, let's, yeah, did that do anything different? Yeah, okay, I don't know. Okay. Okay, so anyway, this is working. I want to implement this in JavaScript. And so this is a very hard algorithm. Actually, it's not that hard. It's just new, and there's some weird stuff to it. So I'm going to go ahead and do it. So let me get myself set up. And I'm going to, here I am. I'm going to, having this fan is so great. Everything is so much better. Okay. I'm also curious, like, let me just try a couple things here, by the way. I'm sorry. Let me try some stuff here. Let's make this much bigger. Interesting. And now let's also, I want to see what happens if I add, where do I choose? Like, let me add like 1,000 points. Yeah, I think I've done this correctly. I think 2D you get some weird results, and the square you get weird results. A lot of points, right? Because I'm definitely getting, and this is sort of like veins too, and blood vessels. I think I've done this correctly. So I'm going to leave this at 1,000. And let me actually, let's try making a circle of points instead, just to sort of see. So where I make all the random points, new leaf, where do I do new leaf? In the leaf object, sorry, this is all like one. Let me fix this, by the way, to make separate tabs. I don't know why I did tree. And then leaf. Nope. Leaf. Should still work. So in the tree constructor, I make a whole lot of new leaves, and each new leaf is a random point. So let me make I'm going to make a random vector, multiply by a width, and then I'm going to, then I'm going to offset it by the middle of the screen. So now the points should be, whoa. Do I have a translate already somewhere? Or something? Tree. Does the tree translate to somewhere? No? Hold on. Where are all the points? What did I do wrong? New leaves. Let me see. Oh, leaf. What did I do wrong here? A random vector multiplied by width divided by 2, offset by the middle. Oh, duh. Multiplied by random. They're all along the edge. I want them to be all randomly around in the circle. There we go. This is what I wanted to do, to see what I get if I kind of have a circular pattern like that. It'd be interesting actually then to start the tree in the center. So I think I did the algorithm correctly. It sort of does appear to be behaving like I expected to. Let's start the tree in the center. Yeah. And what's the length? What do I have as the length? Is that in here, or is that a global variable? Oh, I have a branch class too. Yeah. Sorry, everybody. I'm just kind of wrapping my head around this. Yeah. So you can kind of see this working, doing things based on that minimum and maximum distance. And you can see here, that's that weird thing that happens of sort of being equidistant. And the minimum and maximum, like what if I make this 1? Oh, it's like the leaves don't go away. What if I make this 50? Yeah, I don't know why it stops with such a low minimum distance. I feel like I must not be measuring the distance correctly somewhere. But maybe when I do it again, I won't have that problem. I feel like the maximum distance shouldn't need to be so high. Okay. Okay, so I think I want to go through and explain this and program this now. So, oops. And then do it in 3D. Okay, so let me come back, processing. And I would like to do is make this much bigger and start the tree. I think I'll start the tree again from the bottom. And interesting to see what happens here. And then make it grow a little bit faster. Okay. And let me give myself, sorry, last thing here, 2,000 points. Okay. Okay, so here we go. Yeah, I think I'm getting an effect that's reasonably close to those. Except the distance, something is wrong. Because why should the maximum? I swear this is going to make me crazy. I'm going to be working on this tonight, after I. Because look at this. Now if I make this 600, the distance is somehow measuring still from the bottom, which is very weird because now it makes it to the top, which it shouldn't matter. It should just be about somewhere in my code there's a bug. But I'm going to ignore that for now because I'm going to be building this again. And maybe I'll solve that bug when I build it again or not. Right? I agree. Okay. Okay, here we go. Yeah, you guys are asking the right questions in the chat. Is the distance measured from the beginning? It should not be. Let me go peek in my code. Let me go peek. You know, I'm 3 hours into this. I can take a minute to look around here. So let me make this a little bit bigger. Let me look at where I'm doing the distance check. So this is happening in this algorithm. Leaf.position to branch.position. All the branches. I mean, though, but, and then I get that magnitude. If it's less than minimum distance, fine. If it's greater than maximum distance, if it's less than minimum distance, don't do anything. If it's greater than maximum distance, also don't do anything. So, but this is right. The leaf position with the branch position. Are the branch positions, so let me look at this branch object. The branch can be, this is only for the root. So when the branch gets a parent, it gets, its position is the parent's next position, and then the parent's direction. So the next position is calculated as its direction multiplied by the length, and the next position is add that vector to its current position. I want to draw, there must be, is there a, where do I display? Yeah, and these are the, so I want to just do something here. Just going to look here. Yeah, the segments are moving along. You can see all the little dots in between each segment. So I think I'm doing it right. I don't know. So I'm really going to have to investigate this later. But right now, let's, I'm going to implement this in JavaScript. Okay. All right. Let me check my battery power here. This microphone says 2 bars. And the other microphone I have also has 2 bars, so that's good. So I think I'm okay power-wise. I am going to clear this whiteboard. I'm going to clean this. And this is this probably should be in multiple steps. This is probably going to be about a half an hour, if not longer, to create this. Okay. The closest does not equal null check runs even when the leaf is to be destroyed. Thanks, Oliver. Let me check what Oliver just mentioned. Where is that? Closest. Okay, do you mean this right here? Wait, the closest is not equal to null. So closest always, for every leaf, closest start at null. But this is fine, even when the leaf is to be destroyed. No, closest should be null if the leaf is to be destroyed. I think. I gotta, let's just give this a try. What's the worst thing that happens? Okay, here we go. Oh wait, I'm not set up with my JavaScript program. Okay, so sorry about that. This will just be 1 more minute. Oh boy, 2.5 hours we've been going today. It's like a record here. Oh, that's okay. Let me get this one. Oops, make a copy of this. And open this in Atom. Where's Atom? Here it is. I feel like I should, just to try to keep this video tutorial a little bit shorter, I'm going to create these objects that I know I need in advance. I need a branch, I need a leaf, and I need a tree. And so I need a Oliver is saying something, probably that's right. But I can't, my head can't wrap my head around it right now. Branch, tree, leaf. Okay. And Okay. Okay, here we go. Okay. Okay, yeah, I have looked into livecoding.tv. I would actually be interested in trying a stream through that as well. Okay, space. We are going to colonize space. How do you guys feel about that? It is time to colonize space. Let me just see. This paper is from 2007, algorithmicbotany.org. And there's also, this is a tutorial from 2011. I don't know who, from seaofmemes.com. So, okay. So I'm going to mention these two things. Okay. Okay. Here we go. I should include branch thickness. All right, let's see how far we go with this. Here we go. Welcome to one more coding challenge about trees. And in this coding challenge, I'm going to use an algorithm called space colonization, which does not have to do with colonizing space, although that would be interesting. It's really about colonizing a two-dimensional space of leaves in the screen, and you'll see how that makes sense as soon as I start to diagram this out. So first I want to mention this algorithm is from a 2007 paper that you can read on algorithmicbotany.org. I'll include a link in this video's description. There is also a tutorial that I used in preparation for this from the Sea of Memes website, and I will also, which goes through this space colonization algorithm, and I'll also include a link to this particular tutorial as well. So I'm going to do it in this video simply in 2 dimensions in JavaScript. That's a processing version that I already made earlier this morning. I'm going to program it again from scratch in JavaScript. And then in a separate video, I'm going to extend the concepts into 3D to see if we can create a tree in 3 dimensions. So first, before I start programming it, let's just talk about what this algorithm is in a very general way. So most of the fractal tree type algorithms that I've done in previous videos or that you may have seen work with this sort of methodology of always growing from the bottom. A branch grows from the bottom and it branches and it branches and it branches, and et cetera, et cetera, et cetera. We saw an L system is a very similar thing about starting from a point and following these drawing instructions to kind of spread yourself out around the screen. The way the space colonization works is, let's say this is your canvas, and you have some volume, some little area, and you can imagine like creating something sort of tree-like like this that is filled with leaves. And the leaves are represented as dots. So in other words, in a way, instead of growing from the bottom and reaching the end, this algorithm starts with the end. Like just a random sea of dots, those are all the leaves. Then what happens is you create these segments, and each segment is attached to another segment. And once a segment starts to get close to leaves, it becomes attracted, almost like gravitational attraction to those leaves. And when it gets attracted to a leaf, it spawns another branch, which then, as it goes more for our segment, which as it goes more forward, might start to get attracted to another branch. So, this is sort of the basic idea. And as I start to write the code and get the code for the branches, the segments, the branch segments, and the tree and the leaves going, we'll start to see a little more of the nitty-gritty of how this algorithm really works, and I'll come back to this diagram. So let's come back over here, and I'm going to go to the browser. This is what I have so far. It's a blank canvas, and I'm going to go to my code. And all I have right now is setup and draw. But I've already created, by the way, a whole set of other JavaScript files that are empty. But I know I want to have a leaf object, I want to have a branch object, and I want to have a tree object. So the first thing I'm going to do is write a constructor function for a tree. And in that tree, I'm going to have an array of leaves. And when you first make a tree, I want to create, and let's just start with 100 leaves. So I need some way of creating all the leaves at first. So I'm going to say this.leaves.push a new leaf. So the very first thing I need to do is just create all of those leaves that are going to be in the canvas. So I've got that. And now, in leaf, I now want to write a function for a leaf. And a leaf is just something with a position. So this.position equals create vector. And what I'm going to do actually for simplicity is just make a random location in the canvas. So the very first thing I do is I just create a leaf object that has a position vector. And the tree object makes an array of 100 of those leaves. And I could also have a function here like this.show. And I could say for all of the leaves, have each leaves index I. So to draw the tree, draw all the leaves. Okay, so that means now I have to go to the leaf and write a show function. And in this show function, I'm just going to draw the leaf as a circle at this.pos.x, this.pos.y, and 4 by 4, and maybe the leaf here for simplicity is white and it has no stroke. So if I run this particular sketch now, I still see nothing. Why do I see nothing? Because what I need to do in my main program is I need to say, I'm going to actually have a tree, and I'm going to make, in setup, I'm going to make a new tree, and then I'm going to say tree.show. Okay, leaves is not defined, tree.js.10, and this is what I've forgotten, is this.length and this.leaves show. Okay, so you can see this is how I could start. I could start with just random leaves. Now, how the tree is actually going to look, where you place those leaves randomly can really make a difference. Are they within a box? Are they within a circle? Or within kind of like a heart shape? So there's a lot of possibilities there, but this is kind of the basic idea. And we could see what happens if I create 500 of them. Now there's many more leaves in the window. So now what I need to do next is create a branch, the root of the tree. So I need to figure out what goes in these branch objects. So the branch objects, have I been in the wrong place the whole time? No. The branch objects are these little segments. And the way that this is going to work, here's an implementation that you could do, is you could create a branch object really just only as a position. And then when you make a new branch object, that new branch object also has a position, but it also stores a reference to its parent. And if it knows a reference to its parent, that segment can always be drawn as a line between its parent and itself. So each segment is really just also going to be a dot. So we're going to start with that. So what I'm going to do is I'm going to create a branch object. And the branch object is also going to have a position. And it's going to have a parent. So its parent is another branch. So its position is probably something that I'm going to want to get, maybe as an x and a y, or even better yet, as a position. And its parent I also want to get as a parent. So look at this. So I want to create, whenever I create a branch, I want to give it a position and the parent it's connected to. Okay, so now if I go back to tree, in addition to creating a bunch of leaves, what I want to also create is the root of the tree. So the root of the tree is a new branch. And where should it start? It can really start anywhere. I'm going to weirdly start it in the middle of the window. I think that might be interesting. And so I need a vector. So I'm going to say var position equals create vector in the middle of the canvas, width divided by 2, height divided by 2. And I'm going to make a branch at that position. And the root of the tree, what's its parent? It has no parent. So I'm going to just say null. So the root is a kind of special case in which that it has no parent. So I'm going to have that root. And then I also want to have an array of branches. And I want to take that root and add it to that array of branches. Okay, now, the question, oh, and you know what? I totally forgot something really important. So by definition, the way that this attraction algorithm is going to work, imagine there are like 3 leaves here and I have a branch here. The branch, by definition, needs to have a direction that it's pointing. Because the next branch is, and really I should use the word segment, the next segment is going to be added at the end, and it's going to get a copy of its direction, but it's going to get pulled toward the closest leaf, which is what's going to cause this kind of meandering of all of these segments. So what I need to do in addition is give, where am I? I need to be in branch. Each branch needs to have a direction. So the direction is also something that I can get from the constructor. And so when I make that root, I need to, and where do I do that in tree? I need to also give it a direction. So I think the order of my arguments here is a little bit weird. I make a new branch, add a position, and then and null is the parent. Let's go look at that again, sorry. So position parent, let's put the parent first. So I'm going to, let me come back here. And I'm going to say, sorry, tree branch. I lost this. Where am I? Tree. I'm going to say position. Null is the parent. That's the position. And now I also need to give it a direction. And I'm just going to arbitrarily have it pointing up. So this would make sense, especially if I have a root of a tree like pointing up. So I want to have that tree pointing up. So one thing that I need to do is, here's a key. There's a key set of, there's a key piece of data in this algorithm. There's a lot of pieces to this algorithm. But key piece of data are something called a minimum distance and a maximum distance. And if you read the paper, this will be described in the paper. The idea here is that later you're going to see that I'm going to be looking at the leaves. And I'm going to look at the leaves, a leaf's distance to various branches, various segments that are in the system. And the leaf, for it to be relevant, has to be between that minimum and maximum distance. If it's too far away from any branches, it doesn't play a role. If it's too close to a branch, it's actually been reached and it's done. So one thing that I need to do when I start, if I only have this single branch, I need to make sure that branch is at least within a maximum distance of one of the leaves. So the first thing I want to do is add this maximum distance variable. And I'm just going to say like a big number for now and a minimum distance and a kind of a small number for now. So I'm going to say 510 is kind of arbitrary numbers that I'm going to pick. What you choose for these values can really affect the system. And then what I'm going to do in this tree constructor is I'm going to say, OK, I made this root. And what I want to check is what is the distance? Oh boy, there's a lot going on here. P5 vector dot distance between the root's position and any given leaf. OK, so I need to loop through all of the leaves. OK, I need to loop through all of the leaves. Leaves index I dot pos. So I need to check the distance between the root's position and the leaves position. And if the distance is less than max distance, then we've got a branch that's close enough to start doing the algorithm. So I want to say var found equals false. And then I'm going to say found equals true. And actually what I want to say here is current equals root. Because what I'm going to do is I'm going to say while not found, keep doing this. So what I'm going to do here is I'm going to say I want to like check this beginning root. Like the tree's going to keep growing just in a straight direction until it's close to some of those leaves. And this you'll actually see in most cases, we'll do this later, all the leaves are at the top and the root starts from the bottom, so it's just growing straight up until it reaches the leaves and starts to fan out. So I start by assuming it's not close enough, but if the distance is less than max distance, found is true, and this while loop should stop. But if it is not found, then I need to make a new branch. And how do I make the new branch? I can actually take that root branch, right? Remember, a branch, this is tricky. A branch is a position and a direction. So what I want to do is get a next branch, a next segment attached to it, which would be this new position and a copy of that direction. So what I can do is var branch equals, and what I want to say is current.next. So why not just have the branch itself give me the branch that's attached to it? So if I go to the branch, I could write a function. And this is kind of recursion here in a way. Next is a function where, what does it need to do? It needs to make a new branch. Next branch is a new branch. And where is that new branch? So first of all, the next branch is its parent, is this particular object. That's its parent. Its position is this particular branch's position plus its direction. So I need next position equals add this position and this direction. So next position, and then its direction is just also this branch's direction. But I want to be careful about this, and so I'm going to call the copy function, because I want to make a copy of the vector in case various branches change their direction. The original one should keep their original direction. So then I can say return next branch. So what am I doing here? If I go back to the tree, what I'm doing is I'm getting the next branch, and then current equals, current now equals that next branch. And I also want to say branches.push current. So this is what I'm going to do. Now, I'm not sure I 100% got this right, so I need a way of testing this. So first of all, let's just run this. So branches is not defined, so I have some errors. So I guess I decided I was going to, okay, so I can never remember to say this. So anytime I refer to branches, I need to say this. Leaves is not defined in line 20, so I need to say this dot leave and this dot leave. And cannot read pause of undefined in line 21. So what's undefined? This dot leaves index I dot pause. So let's look at the leaf. Leaf has a pause, so that shouldn't be undefined. Current is the root. So hold on, let's just do console.log current.pause. So that doesn't seem to be undefined. Leaves index I dot pause. Leaves is not defined. Oh, of course, it's this dot leaves. How come I can't ever remember this? Oh, but I have that correct here. So it eventually got to a point where it can't read pause of undefined. Why is, so let me look at tree, is undefined. Okay, everybody. Tree, why is tree undefined? Tree should not be undefined. Tree is a tree object, tree.leaves. Timeout, I'm debugging again. I lost track of what's going on. I forgot something in the for loop. Okay. Oh, thank you. Thank you. So this should get cut back quite a bit when I got stuck. Whoops, back. I had forgot a little bit of code in the for loop there. So let's take a run this again. Should see. Okay, so I don't see anything here because I'm not actually drawing those branches. So let's go through now and say also for var I equals 0, I is less than this dot branches dot length, I plus plus. And what I want to do is say this dot branches index I dot show. So I want to draw all the branches. So I need to go to the branch object, and I also need to add a this dot show function. And now, as long as parent is not equal to null, so remember, this is only the root doesn't have a parent. What I want to draw is a line from this dot position dot x, this dot position dot y, to this dot parent dot position dot x, this dot parent dot position dot y. So let's make this line white, and so now if I run this again, let's see here. Now let's change this around a little bit. What I want to do is actually have the tree start, the root start from the bottom, and let's actually also have the leaves get a random location that's about 100 pixels off of the bottom. So in this case, we should see the branches being attached to themselves up until they get within maximum distance. So, although maybe the first one is my maximum distance is so high. Yeah, so that worked. So you can see here now, this root is going to go all the way up until it gets within a certain number of pixels of one of those branches. Okay, so now once that's done, that's the thing. So let's just review what we've got so far. The only thing we've done so far, let me come back to this diagram, is start with, and I'm going to draw this again over to the right. We've started with segments that are approaching the leaves, and once one of the segments gets within minimum and maximum distance, we need to do something different. Okay? Then we stop. So we're really just working on getting the root of the tree in place. And once we get the root of the tree in place, this is where things start to shift. Instead of working from the branches, we're actually going to work from the leaves. Okay, so let me come back over here. And now what I want to do in the tree, so this is all the stuff that's kind of happening just at the beginning, just to get the tree sort of set up. And now what I want to do is add a function called grow. And in the function called grow, I want to look at all of the leaves. So we're going to go through every single leaf. Var I equals 0, I is less than this dot leaves dot length, I plus plus. And I want to look at each leaf. So each leaf is this dot leaves index I. For every leaf, what I want to do is figure out what is its closest branch. Does it have a closest branch that's in between the minimum and maximum distance? So here, what I need to do is say var j equals 0. J is less than all of the branches dot length, and it's this dot branches, j plus plus. And before I do this, I need to figure out a couple things. I need to, what I'm looking for is the closest closest branch. I'm going to assume that to start that there's no closest branch. And I also might need the closest direction. So the direction of the closest branch. But that's in the branch. I don't need to worry about that right now. So I'm going to look at every single branch. Okay. So the main thing I need to do is look for the distance. This is really hard. This is very long. I don't know if this was such a good idea, this particular algorithm. Should have done this in multi-parts. Whatever, this is how it's going today. Okay, so what I need to do now, I'm looking for the closest branch. So I have to find the distance, right? The P5 vector distance function gives me the distance between two vectors. So I want the distance between the leaf's position, and I'm also going to just make a separate variable called branch, which is this dot branches index j, and that branch's position. So a couple things. If that distance is less than minimum distance, so leaves only exist to attract branches toward them. Once a branch has reached a leaf, that leaf is no longer in play. So we have to mark that leaf for deletion. So I'm going to say leaf, it's reached. Leaf.reached equals true. So that means I need to go back to the leaf object and add a variable called reached, which is false. And we'll use that for something later. So the main thing I need to do here in this particular tree, in this particular part again, okay, I'm looking for the closest branch. But if I happen to find a branch that's too close, I'm done. Leaf is reached, break. And I think I might have, when I was doing this earlier, I think this might be an indication of the bug. There was a bug in my code previously, and I think maybe this is where it was. But we'll find out. Now, otherwise, else if distance is greater than max distance, then also forget about it. This is something to be ignored. If it's still greater than max distance, forget about it. This particular branch should be ignored. Actually, no. I shouldn't break because I want to check other branches. So I don't need to break. I just don't want to include it as anything relevant. Else if closest branch is null. So if it's not too far away and there is no closest branch yet, guess what? It's the closest branch. So that means closest branch equals this particular branch. And what do I need? I need a record, right? That record distance, because I want to know if I find another branch that's closer, is it even closer? So I'll make up some really big number to start with. That's kind of ridiculous. That's plenty big. And then the record is that distance. Now, otherwise, last thing, else if distance is less than that record, right? If closest branch is not null and it's not greater than the maximum distance, if distance is less than that record, then guess what? We have a new record and a new closest branch. So you can notice here that I'm doing the same thing, right? If it finds something that's null and it's not greater than the maximum distance, there we go. I really think that was the problem in my previous code. And then otherwise, so both are the same thing, so I can actually put an or here. If you notice, like if ever like these two elses do exactly the same thing, if it's null or if it's less than record, then this I can shorten this. So I'm going to do this. Okay. So here we go. So this is this whole entire algorithm. For every single leaf, I'm looking for the branch that's closest to it. And it has to be between the minimum distance and the maximum distance. So the question now becomes, for every leaf, after we've looked through all of the branches, what do we do? What do we do if closest branch is not null? That means we found something. That means what we need to do is make a new branch with a new direction. Time out, pause. This is an edit point because I forgot. I have to like go back and look at this. So let me look at this is like a really long, complicated program. Let me look at this one and remember what it says. Remove the leaf and skip it. Track the closest branch segment and the direction and distance to that segment. Oh yeah, so I need the distance to the leaf. Normalize the direction, then add it to the grow direction and increment the grow count. Got it. Oh my God, what a confusing mess this is. People, you guys have interesting things in the chat. Maybe it should be closest branch. Did I do something wrong? Oliver is doing a great job of following along. I think I have this right so far still. Because this is only it's gonna be null if it's too close, because this just gets us out of checking. Oh no, it won't be null. This, I need to force it to be null, because what if it finds a closer one after it finds a farther one? Ah. Everybody has to go. What? Nobody wants to stay more than 3. I can't believe we're doing this for 3 hours. This is completely insane. Okay, I got to come back to I'm going to come back from my edit point. I think I realized I'm missing a piece here. The break I removed fixes your previous bug. Yes, I think it does. But I think I might also need, to set it to null here, because what if it finds a close branch before it gets to the minimum distance one? Yeah, I should probably use this. It's kind of fine either way. Okay. I'm gonna come back from the edit point and keep going, because I think I have a sense now. Oh, camera got moved ever so slightly. My green screening is off. Okay. 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 Line 41. Yes, it should be null as well. Okay, thanks, Oliver. But it doesn't cause issues. Okay, maybe I'll leave it out for right now. Okay. Okay. Okay, I got to come back. I have to pee. I have to take a pee break in a second. I'm going to keep going now. I'll be fine for a little bit longer. This is going to be a long one. Boy, I don't know what I'm doing with these videos and these like long, complicated algorithms. Okay. Doesn't it, if you check, does it, oh. If it's, oh yes, thank you. This needs to be equal null. Yes. I need to check if it's null. Yes. Thank you. Yes, okay. Back from a momentary, okay, hold on, time out. I'm trying to make this easier for the editing. Back from a momentary pause, I realized I had a mistake here that was going to cause me a problem. I actually want to check here if closest branch is null, right? So I want to know if it's less than the minimum distance, then this leaf is over with. And in fact, I want to get out of this loop, and I want it just as a like even doubly safe thing. Let's just make sure it can't have a closest branch, this particular leaf. Although that doesn't actually really matter. Wait, hold on, start up. I can realize why that doesn't matter, because, no, maybe I should put that in there. I know, you guys, thank you guys for your help. Okay, back, I'm going to try again. I'm going to put that in there. Back from a momentary pause, I realize there's a very big crucial error in here. The thing that I'm checking, right, I'm trying to find the closest branch. And the way that I know I haven't found a closest branch yet is if closest branch is null. So this should not be checking if it's not equal to null. This should be checking if it's equal to null. And I could use 3 equals or 2 equals. It's a little bit interchangeable in this spot. Down here, later, I'm going to check, did I actually find a closest branch? So now I have this segmented out. If this particular leaf is so close to a branch, the leaf is done, and also this, I can also just be safe about this and set closest branch equal to null. If it's greater than maximum distance, do nothing. And if it's in between minimum distance and maximum distance, then is it actually the record at this point? If it's the first one, it is the record, or if its distance beats the record, it is the record. Okay, once we have that, we now have our closest branch. So when we have the closest branch, we need to do something. We need to create a new branch or a new segment. And let's look at how that works. So here, I have an existing branch, this particular branch. And I have, this is an existing leaf. And this leaf is the one that's determined to be the this branch is closest to this leaf. What I need to do is get this as a direction vector, normalize it, right? I want it to be of length 1. Okay, hold on. Let's not worry about the normalizing it for a second. I need to get this as a direction vector. Essentially, I want to add a new segment, but I want this leaf to essentially attract it. I want it as if this leaf is pulling on the next segment. So instead of the next segment just going straight up, it goes this way. It doesn't go directly to it. This is like a force that's pulling it in that direction. Because here, if this continues, the next segment is going to pull even more. And eventually it's going to get so close that this leaf will then get deleted. So that's why I'm going to get these nice curvy, veiny looking paths. So how do I pull it? A way of pulling it is normalizing it and then adding it to this particular direction and then putting that at the end here. So let's look at how I might do that. So here with closest branch, what I need to do is create a new direction, which is subtracting. What am I subtracting? I'm subtracting that particular leaf, right? I'm on a particular leaf. That particular leaf's position minus the closest branch's position. And then I'm going to normalize it to make it of length 1, just as sort of a generic, and I could scale it in different ways. You could try different things to play with it, but I'm going to normalize it to make it length 1. And then what I'm going to do is create a new branch. Pause. another edit point. Okay, I need a break for a second. I mean, I can't believe that I've been doing this for over 3 hours. I'm pausing right here because I really just have to go pee. Since it's been 3 hours, I've been drinking water and tea. So I wish I could play music for you guys. But instead I'm going to say this. You can enjoy and chat amongst yourself. Oh, so line 38 is an issue? Okay, when I come back, I'll look at line 38. I'm muting my microphone for a second because I don't want to have the hot mic while I'm using the facility. Now I'm muted, I'll be back. Okay, I'm walking back now. I'm almost back into the room. I think you can hear me. Can you hear me? I see a green. Oh my God, it's so hot in here. Okay, now you guys were telling me that there was an error on line 38. Closest branch, equals null. Okay, I'll have to fix that in my, everything, okay, so, all right, so let me just, now I have to get my head back on and remind myself how I did this in the processing version. Let me close this. And so what I do is I normalize it, add the closest direction, add it, and I have to increase its count. And then if any of them have a count greater than 0, then I create a new branch. with, its direction does change. Closest direction normalize, closest direction add. Oh yeah, and then increase its count. Okay. This is how I did it in the processing version. Okay. 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 So I don't make the new branch right here. Okay. Okay, I'll be back. I'm going to cycle the cameras while I'm here doing this. This is going to get done for better or worse. I don't know about today. I kind of went off the deep end doing these like really complicated things from scratch in one video. Let's see how it goes. Is there still something I need to pay attention to? Okay. True must be null. Okay. Back again after an edit point. I did have a problem here. This, by the way, closest branch, I meant to set that to null, right? Not true. The point is, if it's within that minimum distance, it doesn't count, set closest branch to null. Now down here, what I need to do again, I'm back here, I'm back thinking of this, I needed this branch's direction to get pulled towards this particular leaf. So what I want to do is say, take that closest branch, and then I want to take its direction and add this new direction. So I used the direction variable way too many times. So I'm going to call this new direction, just to be less confusing. And I'm taking that existing branch. I found the branch closest to that leaf. I got the direction. I found the branch closest to that leaf. I found its direction. I found that direction, and I'm moving its direction toward that. And the other thing I need to do is the branch then, part of this algorithm is actually having the branches have a count variable. So the branch needs to count how many times it's been found near one of the particular leaves. And we're going to see this later because this is going to be important because I want to average all of those sort of forces together. So what I'm going to do here, so I add a count variable, and then I say closest branch dot count plus plus. Okay? So let me recap that. This is pretty confusing and tricky to see if I can make this make sense. I have a branch which has a position and it has a direction. And I have a bunch of leaves. So let's say if I'm going to show you these two leaves. So this leaf finds itself closest to this particular branch. So what I do is I make a vector that points from here to there. I shrink it down and I add it to the direction. So now this branch's direction is kind of going like this. Now later I might find this particular leaf is also close. So I need this particular vector and I add it to that. It comes back over here. So these branch, as I go through all the leaves, I'm pulling various branches, segments that might be close and like stretching them. So not stretching them is the wrong word. The pen cap went, but pulling them as if it's a force. Okay, so this is now done, right? This part of the algorithm is done. I'm looking at every single leaf. The leaf, if it's less than minimum distance from a branch, for every leaf I look at every single branch. If it's too close to a branch, we're done with that leaf. If it's too far away from the branch, that branch is not a candidate. If it actually is the closest one, I'm going to keep track of it, and that branch is going to be attracted to that particular leaf. So once I've done that, now it's our job to do the following. The first is I need to go through and find any leaves that were too close and delete them. So I'm going to loop through, and I'm going to loop through the leaf array backwards. Because deleting things from an array, you need to loop through it backwards because you're taking stuff off the end so as to not mess it up. So I starts at the end of the array, goes down to 0, and then I minus minus. So, and I'm going to say if this dot leaves index I was reached, remember I have in the leaf object, I have a reached variable that's set to false. And what do I do in the tree? If it's within the minimum distance, I set that reach to true. So then later I can go through in a separate loop. I could have done it in the loop above, but just for simplicity, I'm doing this in a separate loop. I can then say this dot leaves splice delete one element from the array at index I. So that's the first thing I can take care of. The next thing I can take care of is I need to go through all of the given branches. So now I need to look at every single branch. And I need to figure out what branches were attracted to what leaves. So how do I know if a branch was attracted to a leaf? Well, I know if its count was increased by at least 1. So branches could be attracted to leaves 0, 1, or more times. And I only care, and I'm going to say var branch equals this dot branches index I, just to make my code a little easier to work with. I only care about branches whose count is greater than 0. And if their count is greater than 0, what I need to do is make a new branch attached to it. So how do I do that? So the first thing I need to do is I need to actually average, I need to divide by count, because I was adding all those vectors to it. And if it was near 10 different leaves, then I want to divide by 10. So what I should do is take that branch's direction and divide it by that branch's count. So that's a way of averaging however many branches I was sort of attracted with a force. And then I want to make a new branch. So if I make a new branch, I always need 3 things. I need the branch's parent. The new branch's parent is that existing branch. Then I need the branch's position, which is that branch's, the parent's position plus that branch's direction. So new position equals equals add the previous branch's position with that branch's direction, and that's the new position, and then also the direction. And I'm going to copy it. Now I have some redundancy here, because honestly, if I could actually write a function in the branch object to produce the next branch, and I did that actually in a previous processing version of this that I didn't. But right now, this is where we can see what's going on here. I have to make a new branch, right? This is a branch that's growing. Its parent is the previous one. It gets a new position based on that new direction, and also it's got to store that direction in case it connects to it starts being pulled towards leaves as well. And then I should just be able to say branches. This dot branches dot push new branch. Well, someone's telling me line 66 I forgot to add. Thank you. So this should add those two. Thank you very much. Okay. So let's. I think that's kind of everything. This is the grow. This is the grow function. Let's just run this and see if I have any syntax errors. So this still looks about right. But I didn't actually call the grow function. I'm a little bit afraid to. I added a ton of code. But I'm going to add that grow function now in draw. I don't see anything happening. OK, so we got to figure out what am I missing here. At least I'm not getting any syntax errors. Let's first at least see if grow there might be getting stuck in an infinite loop somewhere. So in the tree function, I'm going to just console log growing. So let me just make sure this is getting called over and over again. OK, so I'm not stuck. Things are looping. Oh, the count has to be reset. So I forgot something very important. Each generation, I've got to reset the count. And also, actually, the branch should have its original direction. It shouldn't change. So this is great. I forgot an important step. No wonder I don't know if this is what's causing the problem, but I certainly didn't forget a really important step. So branches have to be reset. So one thing I want to do is say original direction equals. So I always want to keep a copy of the branch's original direction, because after a branch's direction gets manipulated in order to create the direction of the next branch, I knew I forgot something. I need its direction to go back. and I need to copy it again. So I need to restore its direction. I could probably, after I do this, I could probably go through the code and find extra places where I copied vectors, but I have to be very careful that I don't by accident have vectors pointing to the same data, changing it one place, it changes it to another place. And I also need to reset count by 0. So what I need to do is after, at the very end here, when I go through all of the branches, I need to once again, and I should go through the branches. This is bad, by the way. I'm surprised that this didn't cause a major problem, because I'm going through this array of branches and adding to the end. So here I also want to start at the end of the array and go backwards down to 0. And then add to the end. And I can also, just for safety, I can reset all of the branches. So this is definitely something that I missed. What I need to do is, as I'm going through the branches, for the ones that were close to leaves, to create the next branch, I create the next branch and then reset that branch. And so now, okay, original dir is not defined. Where's that in branch.js line 9 so this, by the way, needs to say this.dir. Actually, it kind of worked because that's there. And then this also needs to say this.original. Okay, so promising. This is all still growing. So what did I miss? Okay, so let me look here in tree and see where things might have gone wrong. So let's just see, is this actually happening? Am I finding things? I'm not finding any closest branches. Now, I wonder if there's an issue with my, maximum distance being the same as minimum distance. That can't be good. How did I do that by accident? There we go. Something crazy is happening. Okay, so that kind of worked. I think maybe my distance was too short. This is kind of doing stuff now. Hey, I like how this works. Okay, it's working now. We're getting a nice little tree growing and branches being attracted to leaves and things being spread out. You can see how it's working. I think this is kind of about right. So there's a couple things that I'm noticing. It's actually running quite slow. And something I could do to kind of speed things along that makes more sense is also to have the branches have kind of a minimum length. The length is based on the direction vector, which I didn't actually normalize. I just realized, I think there's some technically some correct way of doing this that I probably missed. So if I go here, when I made the new direction, let me find that. Where is that? Oh, I already had this next function. Look at that. I forgot that I had the next function. So this is actually could be, one thing I could do to improve this, I got this now. Sorry, back, where is that? In the tree. I don't actually need to do this here. I should be able to just say this.branches.push new branch.next. So I should be able to use the next function, which just gives me that next branch based on that. So that I should be able to use. This should be identical. So that saves me, I have that next function, I should use that. And the reason why I thought back to use that is because I should just do this entire video again because I understand this algorithm so much more now from having to be in this very awkward place of programming it live. But what I want to do here is go back to that next function, and what I can actually do is I can say I'm going to make I'm going to multiply this dot direction times 5. Right? So this is kind of like the length. I can actually give this a length. So branches can have a sort of default length, and then I can add that. So if I do that, I know I did that kind of quickly, but what you'll see here is like it's kind of growing much faster now because each branch by definition moves by 5. And I wonder if actually this should always be normalized. I don't know if that really makes a difference. I think it's the same. I think by definition, because I divided by count, it might have been, that's sort of like normalizing it. But anyway. So this is pretty good. So I'm going to stop here because I'm going to do some, I'm going to go back to this algorithm and look at it in 3D and maybe, but here's the thing. So I'm going to post this code. It'll be linked in the description of this particular like incredibly long video. I don't know, it's like 45 minutes long. But really what I want you, if you've watched this, if you've stayed with this, if you're working with this code, somebody in the chat, Oliver in the chat, has made an excellent point, which I'm going to fix before I go on. But what I want you to do is think about how are you arranging those seed leaves? What is your minimum distance? What is your maximum distance? What is your length of each branch? So what types of patterns, leaf, veiny, tree-like patterns, even in 2D, how can you use color? How can you use thickness? The more branches that are layered in the same spot, can you make it thicker? Try some of these ideas, improve on this, and I'll try to come back in another video and kind of make these improvements because I think it would be good to do a follow-up on this. But let me just fix one thing. I don't need to normalize the direction because I divided by count. But where did I divide by count? I divided by count here, but I really should be dividing by count plus 1 because I'm also including the original direction vector, which is a unit vector. So I've added that unit vector with all the other unit vectors of close leaves, and so there's one more there. So that should probably make things more quote-unquote correct. And you can see how this works. So I'm just sort of curious just to play with this for a minute here. Like, for example, in tree, what if I give myself only 50 leaves? You can see kind of what I get there with only 50 leaves. What if I give myself 1,500 leaves? You can see what's happening with 1,500 leaves. And you can see some are getting kind of like, some of these like perfectly equidistant ones are getting ignored, like the branches just go right through the middle of them, which is kind of interesting. But really what would be more interesting would be for me to arrange the beginning. Okay, I have to end this video now. I'm going to move over to processing in the next video and look at this same algorithm and try to extend it into 3D. And at some point I might come back and try to do that in JavaScript in 3D as well. Okay, thanks for watching. Okay. Yes, Oliver, thank you. Oliver, thank you in the chat. Thank you so much. I would not have gotten through this without you correcting me and helping me with all of this stuff. And so I think there were some other people who chimed in. This was really tough. And it is after 5 o'clock. Oh my God, I started this at 1:30. It's 3.5 hours in. I want to do the 3D thing really quickly, which I think, I'm not going to make this a video right now. I'll come back to this next week or another time. I have to close this. I made myself completely insane. But I'm at least going to go look at this processing one that I made. I want to correct that problem that I had. Right? Where was the problem that I had? So I should take out the break here. Wait. How did I do it in P5? So I fixed, whoops. Let me go open, my brain is, I'm so brain dead. I have to not allow myself to do this for this long because it's too much. Let me go back to Adam. I'm afraid to look at my email because I sent a whole bunch of emails about things before I started the live stream. I haven't looked at my email in 3 hours. So wait, hold on. Under tree, I am doing, this is my if statement. If it's reached, true, otherwise closest branch is null. So let me go to processing. Closest is null. Otherwise, max distance, oh yeah, don't have the break there because I want to keep checking. Otherwise, if it's null, that should work. I don't know why I kept this direction because the direction by definition is in the closest. Oh, well, did I need that though? I just did it differently somehow. Interesting. Get that new direction. Oh, because I'm using this. I got it twice. Because I just used the distance function up here and I didn't bother to get that vector. That's fine. So I can, either way is fine. So this now should be fixed. So I should be able to go back to this and have like a maximum distance like this. Yeah. Okay, great. So that fixed the bug in this one. So now I'm just going to do something. How bad could this be, right? P3D. Right? And then leaf, because vectors are 3D, random 3D. Right? Offsetted by the center. That should work still. Everything should work. I should still draw, oops, now these have to be little like spheres maybe. Oh, wait, hold on. Undo, 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 undo. So let's change this. I'm just really curious if this works really easily. Change this to P3D. Oh, you guys can't see what I'm doing. My head's in front of me. So let's just make sure this still works. What did I break? Oh, whoops. Maximum distance 50. Okay. Change this to P3D. Okay, no problem. Now, in leaf, the first thing would be get a random 3D vector. And whoops. And I can still just draw it as a ellipse facing forward. In 3D. But let's do it as a point. Because what I can do is stroke weight 4 and push matrix, pop matrix. So let's also add, let's import PZCam. And PZCam is a library. Just checking to make sure there's no urgent text that I have to. Oh, and then I can point it to the center. Right? How do I do, what do I need? And then I need like, isn't that all I need for PZCam? Yeah. Whoops, but everything is off. So now everything can be 0, 0. So I don't actually have to, I don't have to do this anymore. Okay, so these are all my points in 3D space. Okay, so that's good. Now, the root of the tree then, which I did a little bit differently, should actually start just at 0, 0. Ooh, but it's flat because I'm not doing anything in 3D yet. Or maybe I am and I didn't realize it. This entire stream will live on YouTube forever. Assuming YouTube doesn't mind that it's 4 hours long. I can't imagine that it does. But I am recording a backup of this. So I will post the whole thing. And the 4 videos will get uploaded as separate edited chunks. 2000 is insane. Let me just do this. Okay. So how can I make this now 3D? So the branches, is it really just a matter of where do I draw? Is it the branches that I draw? Is there a display function in the branch? The leaf or the tree, just where do I draw the lines? Oh, here. So begin shape, end shape. Vertex, b.pos.x, b.pos.y, b.pos.z, and then b.parent.pos, b.parent.pos, and b.parent.pos. Let's see if that works. So why am I not seeing begin shape, end shape? What did I miss? Stroke is there. Right? Let's look at, shouldn't that work? Vertex takes 3. I don't have to use translate for that. What did I miss? All vectors need a z. Yeah, but the vectors all have a z by definition. All the math doesn't change. Did the z was started at 0. So when I created this new, the z, this shouldn't matter. What happened here? Something happened here. Let me zoom away further. You can see that the leaves were disappearing. And I'm just not seeing the result. Hold on, I just want to just make a random thing here. And how many, let's make more leaves. Right? They were all disappearing. The color, is it, but I thought I have translate, let me look back under tree. So let me just do something just to be sure. Let me do a point just at the branch locations, and I'll make those red. Yeah, okay. So it is definitely working. What did I miss with begin shape and end shape? Why can't I just draw a line? Well, let's do parent. Let's make this blue. Yeah. I see all the points are there. So what did I miss here? Why does begin shape, end shape? Am I just losing my mind? Let me look at line. We'll just use line. Will line let me, line will let me do a Z. Great. So I'll just use line. Trying to be all fancy here. There we go. Yay! Okay, so you can see what we get with this crazy tree-like thing. Now, can I make this a tree? So what I want to do is actually start from, where's the tree start? I want to start from like Y way down, like here. Yeah, there we go. You know, leaves a little something to be desired, but you get the basic idea. That's pretty cool. So I'm assuming somebody could do something with this. It's a little bit more interesting and think about thickness and think about the shape. But okay, so I think I'm finished for today. I would like to In a way, it was super easy to make that 3D. I almost want to like quickly make that a video. Begin shape lines. Thank you, Oliver. If it wasn't for Oliver, yeah, of course, that's what I missed. Begin shape. In 2D, it doesn't matter. It'll automatically do a path. But you're right. I needed to do a line or lines. Yeah. And I could put more leaves. Yeah. Try adding lights. Oh, thank you. That'll at least make it nicer. Let's do something. You know, or an ambient light. Okay, I'm too brain dead right now. So I'm going to come back to this next week. I'll release this code if people want to play with it. But I think I've got to go since it's after 5. And I'm going to hit stop on this. Thank you guys for sticking with this for so unbelievably long. There's actually 53 people still online watching this. I'm curious to see, you know, Facebook must have cut me off at some point. Because I can't imagine, and Twitch didn't work, which I apologize for. But does anybody have any last comments or questions they want to ask before I go? I was going to talk about Patreon a little bit more, answer some questions, but this is it for now. So people asked about when the next live stream would be. That's a good question. Not the earliest would be Tuesday next week. So so if you want to sign up for, if you're somehow still here, want to come back and watch more, if you go to schiffman.net, you can sign up. You can sign up your email here for updates, and I'll probably send an email out sometime this weekend or on Monday, giving you guys a time for next week. And I might only have one session next week. I did 2 this week, and at some point, you know, this weekend or early next week, some of these videos will come as standalone videos. And I think next week I want to do, and somebody's asking, yes, am I going to do a Q&A like live stream? Yeah, you know, I don't have a good system for this. Sometimes I'm kind of answering questions more, and sometimes I have a plan. And today is kind of, I sort of had a plan that went a little bit off the rails. But I am, for the Slack and the Patreon, I am trying to, in particular, create a system by which people could submit questions or topic suggestions, and I would do kind of tailored tutorials for. And that sort of thing. So thank you guys. I'm gonna say goodbye, and videos will appear. This live stream will, I don't know how long it takes YouTube to process and archive it. It'll then take a while for the description and tags to get written, but those will show up at some point. And enjoy your weekend. If you're in the United States, enjoy your holiday weekend. If you're elsewhere, enjoy your weekend anyway, your regular weekend. I'm completely dead exhausted, and so I'm going to go. Okay, you guys. Thanks for watching. I'm going to hit stop. Goodbye. I will see you. I will send an email out, updates on Twitter for sometime next week. Okay, and say hi to me on Twitter. The best way to reach me is on Twitter, or if you're on Patreon, anybody who's on Patreon, I'm adding to the Slack channel, which we can discuss and this sort of stuff as well. Okay, talk to you soon.